So it's fine now. So how many of you want me to study in Hindi? Want me to teach you in Hindi? Tell me, guys. How many of you want me to teach you in Hindi? Tell me. How many of you want me to teach you in Hindi? Tell me, everyone. If you want me to teach in Hindi, then I'll proceed with the Hindi, and if you want to teach me in English, then I'll proceed with the English. Okay? Tell me. Okay. English. Okay. Anyone else? Tell me, guys. If you want me to teach in English, then I'll proceed with English and conduct a poll. Sahil is saying Hindi. Okay. So there is only one student for Hindi and maximum student are for English. Okay. Harsh Mishra is for Hindi. But okay, please tell me one more thing. Okay. So almost 50-50 is there. But how many of you do not know the Hindi language? Tell me. Is there anyone who don't know the Hindi completely? That I cannot understand Hindi. Okay. So how many students are like this? Tell me, guys. How many students are like this, that they don't understand Hindi completely? And they don't know even a single word of Hindi, or maybe they are not comfortable with Hindi. Tell me, guys. Arun is not, I mean, he cannot understand Hindi. Okay. Anyone else? Anyone else? Because I'm comfortable in Hindi, and the thing is, I can deliver you in, I can deliver much better in Hindi. That's the main reason. Okay. So though I can teach in English also, but I can deliver in Hindi maybe at some better level. So tell me, guys. So there are some students who don't know English, who don't know Hindi. Okay. So let's proceed, guys. Let's mix them together. Okay, let's mix them, Hindi and English, and let's proceed. Okay. So today's session is about DC machine, and it's a long session. It's approximately 3 to 4 hour session, and I hope you will enjoy. In yesterday's class, you have completed. I think Astos sir has taught you about transformer and induction machine. Okay, because transformer and induction machine are more or less same. So from in this session, we'll discuss about the DC machine and the synchronous machine. So the main concept I'll discuss in this session. Okay. So let's start. This is my introduction, and yes, there is one MSQ series is going to start, guys. Very important, because if you are from electrical engineering, let me tell you, from last 2 years, they are not asking MSQ in electrical, but in every branch, like in ECE, last year, there was like 14 MSQ. Okay. So we hope that this year also, I mean, this year they will ask you about MSQs. So there will be some question in MSQ in electrical engineering as well. So we'll start a MSQ series, and you can join this series also. You can attend this series, and this series will start from 17th of January. Okay. So from 17th of January, you can attend this series. Okay. There is one mock test. Okay, for GATE 2023. You can register for that, and you can register. The link is given in the description. So you can go to the description and register yourself for the mega mock test. Okay, and you can check your preparation. There is one mega workshop is going on for GATE 2024 students, and this workshop is on 15th of January, and it is taken by Abhinav Negi sir. So you can recommend to your juniors or your friends who are preparing for GATE 2024. So they can take the advantage of this mega workshop. Let me tell you, guys, one general aptitude session is also there, and it is coming soon. I mean, maybe in within a week you will get the notification of this session. It's again very good. I mean, it's easy. Aptitude is very easy, and you can get 15 out of 15 in general aptitude, and it is taken by Rakesh Talreja sir. So you can join this session. And there is one more session for mathematics, and it will be again, the date will be announced soon, and it will be taken by Rakesh sir and Ankit Joshi sir. So I hope you will enjoy this session. Now it's time for the test series. So better you join the test series by BYJU'S exam prep. BYJU'S exam prep is providing you the test series also. So the test series again, it contains 60 plus tests, and the interface is exactly same like the GATE exam. Okay, like virtual calculator, or maybe the exact interface is there. So you can join this test series, and you can take the advantage of that, and the questions level is again very good. So you can join this test series. Now, those students who have not subscribed the channel, please subscribe it and like the session, press the bell icon so that you get the notification whenever the session will be live. Okay, let's start the session, guys. So let me tell you, I'm not going to tell you each and every point, but I'll tell you the more important points, because the important points, obviously in 2-3 hours we cannot cover the entire topic like DC machine and synchronous. Obviously we can't do that. But actually there are 3 chapters. One is basics of DC machine, other one is DC machine, basics of rotating machine, and then DC machine, and then synchronous machine. So actually there are 3 chapters. So it is not possible to cover all the topics in like 3 and 4 hours. So we'll start with the important topics only. We'll take the important topics, and whatever the important part is, I'll discuss that. First of all, the most important topic is this electrical angle and the mechanical angle. Now you have to understand what is electrical angle and what is mechanical angle, and what is the relation between electrical angle and mechanical angle. So the relation is this theta electrical is equal to P by 2 theta mechanical. Now P is number of pole. Everyone know that. P is number of poles. Number of poles. So electrical angle is always greater than mechanical angle. Okay, electrical angle is always greater than mechanical angle, and this is the relation. Theta electrical is equal to P by 2 theta mechanical. Now this relation is very powerful. From this relation, what you can do is you can calculate, you can derive many other relations. Like if you take the derivative on both sides with respect to time, if you take the derivative, then it will become d theta electrical divided by dt is equal to P by 2 d by dt of theta mechanical. You can write like this. So it will become omega electrical. Omega electrical is equal to P by 2 omega mechanical. Okay, so you can write like this. It means the electrical radian per second will be equal to P by 2 mechanical radian per second. This way also you can derive, I mean this relation will also be very helpful in many places. Now you can further simplify this. You can say that here you can see 2 pi f electrical. This f is electrical frequency is equal to P by 2 into 2 pi f mechanical. Okay, 2 pi f mechanical. Now what is the meaning of f mechanical? Okay, I'll tell you what is the meaning of f mechanical. Let's say something is rotating. Something is rotating. Let's say there is a rotor which is rotating. Okay, so let's take a rotor. I have this rotor, and this rotor is rotating. Let's say this is north and this is south. Okay, and this rotor is rotating. This rotor is rotating in this direction. Now what is the f mechanical? F mechanical means mechanical frequency. Now, how to calculate the mechanical frequency? It is called a revolution per second. A revolution per second. You can also write it n, because frequency means number of cycles per second. Frequency means number of cycles per second. One cycle means one revolution. So the F mechanical can be written as revolution per second, number of cycles per second. Okay, so I can write it like this: small n. Small n represent RPS. So what you can do is you can put this small n here, and F will be equal to Pn by 2. This way you can write the frequency. So frequency, electrical frequency is related to the speed of the rotor, and that is Pn by 2. Now n is in RPS, revolution per second. If I want to convert this in RPM, revolution per minute, okay, capital N, then how to write it? Capital N. Revolution per minute. So that revolution per minute will be 60 into N. Why? Because this is the revolution per second. In 1 second, this much of revolutions the rotor is rotating, and the speed of the rotor is n revolution per second. In 1 second, there are n revolution. Now in 60 seconds, there are 60 n revolution. Okay, so if the speed of the rotor is n rps, revolution per second, then it will be 60 n rpm, revolution per minute. Is it fine? So you can say capital N is the speed in rpm, and you can calculate the speed in rpm as 60 n. So from here you can see that the small n will be equal to capital N by 60. Is it fine, guys? Okay, so what you can do is you can put this small n, so it will be F is equal to Pn by 120, or you can write that N is equal to 120 F by P. Is it fine? So from this relation we have derived, from this theta electrical and theta mechanical relation, we have derived this relation, speed relation, 120 F by P. Now it is very powerful. This relation is very powerful. Okay, N equal to 120 F by P, and this N is in RPM. If you want to write this R in RPS, then N has to be 2F by P. In RPS, you have to write 2F by P. Is it clear, guys? So I hope you understood this relation. Now let's come to one more point. Remember, theta electrical is equal to P by 2 theta mechanical. It is very important. Why it is important? Let's say, okay, I'll come to this point later maybe. So I told you how to write this relation. What is the meaning of this relation? Theta electrical equal to P by 2 theta mechanical, and from this relation you can calculate this. Now you'll ask me, sir, what is the meaning of theta mechanical or theta electrical? Let's say you have this two-pole machine. In this two-pole machine, let's say this is the rotor I have. In this two-pole machine, if you take a conductor at this position, and if this rotor is rotating, then this conductor will encounter some magnetic flux density or magnetic field lines. It will encounter some magnetic field lines or magnetic flux density. Now, if you say that this position is alpha equal to 0, let's call alpha as a mechanical angle. Let's call alpha as a mechanical angle. So if you start from alpha, and if this conductor is rotating, so at this position the flux density is 0. The flux density is 0. At this position the flux density is 0. Okay, number of field lines per unit area at this position is 0. Now if the conductor is moving like this, so flux density will increase, and the flux density will be from north to south. Okay, and I call this north to south flux density as positive. So you can say that if this rotor is rotating in this direction at 90-degree mechanical angle, if this has rotated by 90 degree, the flux density will be maximum. This conductor will be at the middle of this pole, so the flux density will be maximum. Tell me, guys, is it clear? Now after 90 degree, again it will be 0. It will be 0, and then after 90 degree it will be minimum. Tell me, guys, this will be the shape of the flux density. Is it clear? This will be the shape of the flux density. It means you can say that flux density is varying with the space angle, with the mechanical angle like this. And you know that the induced EMF in this conductor, induced EMF in this conductor will be E is equal to BLV. You know that, BLV. This is the induced EMF. So the induced EMF wave shape will also be like this. Whenever this conductor is here, the induced EMF is 0 in this conductor. Whenever it is in the front of this north pole, the induced EMF will be maximum, and then it will go down and like this. Okay, so the induced EMF, which is an electrical quantity, that will also be like the same. So I have plotted B as a function of alpha. Now B is an electrical quantity. Let me tell you, guys, B is an electrical quantity and alpha is the space angle. Now let's increase the number of poles to 4. If the number of poles are 4, then how to plot this B? Okay, so let's plot the number of let's increase the number of poles. Now what I want to do is I want to increase the number of poles to 4. Let's increase the number of poles to 4. Let me write it here. This is my rotor. It is one pole. Okay, so this is north, south, north, south. Now let's start from here. Let's call it alpha equal to 0. You can give any point as alpha equal to 0. You can take any point as alpha equal to 0. Now if the rotor is rotating in this direction, so let's plot B alpha again. At alpha equal to 0, at this position the flux density is 0. Okay, now if the rotor rotates by 45 degree, it will be in front of this. If the rotor rotates by mechanical angle 45 degree, at mechanical angle 45 degree, this conductor is in front of the north pole. It means the flux density will be maximum. Flux density will be maximum. Fine. At 45 degree, at pi by 4 mechanical angle, it is at 45 degree. Now after 45 degree further, if it further rotates by 45 degree, now this conductor will reach to this point. At this point the flux density is 0 again. Okay, so the flux density will be 0 again. This is at pi by 2, mechanical angle pi by 2. So it has rotated by pi by 2. Okay, after pi by 2 rotation it has reached here. So again B is 0. Now after 45 degree further rotation, it will come in front of south position. Is it clear, guys? Tell me. Now it come in front of the south position, so the flux density will be minimum, and then it will go like this. Okay, at this point again 0. Now at this point it will be positive again. It will be positive again, and then it will be 0 at this point. It will be 0 at this point, and then there is one more cycle, one more half cycle, negative half cycle. So you can see that this is my electrical quantity. Flux density is electrical quantity, and if you are moving 360 degree mechanical, it means one cycle you are doing. Mechanical angle is 360 degree, but the electrical quantity, if you look at the electrical quantity, in electrical quantity there are 2 cycles. We have covered 2 cycles. We have covered 2 cycles. One cycle is up to this point. From this point to this point, one cycle, north and south. We have covered north and south, and then one more cycle from this point to this point. It means you have covered 2 cycles in electrical quantity. Electrical quantity you can take as B or E, no problem. You can also take induced voltage also, E. E is the induced voltage in this conductor. So if you are doing one rotation, it means one cycle in mechanical, it will be equal to 2 cycle in electrical. Okay, whenever the poles are 2. So there is a relation of electrical angle and mechanical angle, and this is the relation. You can derive this relation from here. Okay, I hope you understood it, how this relation came into picture. Theta electrical, so the electrical quantity angle has to be P by 2 times of theta mechanical angle. It means if mechanical angle you have covered is 360 degree, then electrical angle has to be 4 by 2 into 360 degree, 720 degree. It means 2 cycle you have covered. Okay, I hope you understood this, how this relation came, and from this relation you can derive these relations. I hope it is clear to everyone. Now let's come to the next important topic, and that important topic is flux per pole. Okay, what is the meaning of flux per pole? Flux per pole. Look, let's say I have a rotor like this, and on this side we have north, on this side we have south. This side is, let's say, north, this side is south. Okay, obviously from north to south there will be field lines. From north to south there will be field lines. Tell me, guys. There will be field lines like this. From north to south there will be field lines like this. Clear? Now I want to calculate the number of field lines per pole. Number of field lines per pole, or you can say flux per pole. From one pole, how much field lines are coming out? How many field lines are coming out? That I want to calculate. So I don't want to derive it. But the flux per pole, I can write it like this. It's 4 by P BP LR. Now what is L and what is R and what is BP? I don't want to derive it because it will be a time consuming phenomena, and it will consume my time, and I don't want to do it. So you can directly write the formula. 4 by P BP LR. BP, what is BP? BP is the peak flux density. BP is the peak flux density. Peak flux density. Okay, BP is the peak flux density that we have already shown in this. This is my BP. Okay, BP is the peak flux density. L means the length of the rotor, because you are looking on the top view or maybe side view. You are looking on the side view. Actually it's a cylindrical shape, so it has some length L. The rotor has some length L. Okay, rotor is like this, it has some length L, and the rotor has the radius R. The rotor has the radius R. So the flux per pole will be 4 by P BPLR. Okay, 4 by P BPLR will be the flux per pole. I hope it is clear to everyone. Tell me guys, is it clear? Tell me. Now I want to ask you, how many of you want me to continue in English? Because I understand that there are some students who has left the class, and now there are few students who are attending. Tell me, how many of you want me to continue in English? Tell me, how many of you want me to continue in English? Tell me. Okay, Raghuram is still there. Anyone else? Arun, because Arun initially told me that continue in English. He don't know the English. Tell me. I think he is not there anymore. Okay, Vetri is there. Okay, Vetri. Okay. How many of you want me to continue in Hindi? Tell me. The Hindi guy. The Hindi guy, tell me. Tell me everyone. Okay. Okay, let's proceed with English. So I told you the flux per pole. So this is the flux per pole. It means it is the total counting of the lines. It is the total number of field lines which are coming out from the north pole. Okay, 4 by P BPLR. BP is the peak value of the flux density. L is the length of the conductor. L is the length of the you can say rotor, and R is the radius of the rotor. Okay. Now there are some situation in which the coils are not full pitched. Now what is the meaning of full pitch coil? Let's take some special terms. One is called coil span. Coil span. What is the meaning of coil span? Number 2 is full pitched coil. Full pitched coil. What is the meaning of this? Full pitched coil or corded coil. Corded coil. Okay, let's try to understand the meaning of this. What is the meaning of coil span or the full pitch coil or the corded coil? Okay, let's first understand this. So what we can do is, let's say you have one rotor. Let's say you have a rotor and there are 4 poles. Let's say there are 4 poles. Can you tell me, this is north, south, north, south. So please tell me, what is the electrical angle between 2 poles, 2 adjacent poles? Mechanical angle is 90, you can see that. Mechanical angle is 90. Now what is the electrical angle? So electrical angle is equal to 90 into P by 2. Okay. P is 4 here in this situation. Number of poles are 4. So it will be 180 degree. You can see that the electrical angle between any 2 adjacent pole will be 180 degree. Okay. Electrical angle between any 2 adjacent pole will always be 180 degree. Just remember this point. Now let's come to the coil. Let's say I have a coil in the rotor. In rotor there is a coil. Okay. And one side of the coil is at this location and one side of the coil is at this location. Because every coil has 2 sides. Whenever you have coil means the turn. If you put the turn, then let's say coil is how do I define the coil? Coil is it's a turn. Simply it's a turn. It has 2 sides. Coil is a turn like this. Okay, so it has 2 sides. Okay guys, it has 2 sides, one side in this slot, one side in this slot. Okay, so coil has 2 sides. Let's say one side is in this slot and one side is in this slot. Now tell me, what is the mechanical angle between the 2 sides of the coil? Mechanical angle is 90 and the electrical angle is 180. So if the electrical angle between the 2 sides of the coil is 180 degree, we call that full pitched coil. Is it fine? Full pitched coil. we call that full pitched coil. Is it clear, guys? We are calculating the electrical angle between two sides of a coil. The electrical angle between two sides of a coil is called coil span. If the coil span came out to be 180 degree, it means the coil is full pitched coil. Okay. If the coil span came out to be 180 degree, then we call it full pitched coil. But let's say there is, let's call it AA prime. This is my AA prime. It is a full pitched coil. Now let's take one more coil. Let's say this is my B point and here you have B prime. In this slot you have the other side of the coil. Let's say there is one more coil, B coil. In B coil also you have two sides. So one side is in B slot and one side is in B prime slot. Now you can see that between these two sides, this mechanical angle is not 90 degree. This mechanical angle is less than 90 degree. If the mechanical angle is 90 degree, then electrical angle will be 180 degree. That's correct. But if the mechanical angle is less than 90 degree, then electrical angle will also be less than 90 degree. It means the coil span of this coil, electrical angle between these two sides is less than 180 degree. So the coil span for BB prime coil, the coil span is less than 180 degree. Okay, it's less than 180 degree electrical. If the coil span is less than 180 degree electrical, we call it coded coil or short pitched coil. We call it coded coil. Okay, so this coil BB prime is coded coil. Okay, now we have one coded coil. This is coded and this is full pitched coil. Now in coded coil, can you tell me the coding angle? What is the meaning of coding angle? What is the meaning of coding angle? Coding angle is by how much angle it is short pitched. By how much angle it is short pitched. Let's say this mechanical angle came out to be maybe 80 degree. Let's say the mechanical angle between two sides is 80 degree. Now what is the electrical angle? So the electrical angle is 80 into 4 by 2 P by 2. So the electrical angle came out to be 160 degree. So the electrical angle between the adjacent side of the coil is 160 degree. This is the electrical angle. Now how much angle is short pitched? Tell me that. Tell me that. So the coil is obviously, the coil span is less than 180 degree. It means it's a short pitched coil. If it is the short pitched coil, what is the coding angle? So the coding angle will be equal to, coding angle can be represented as epsilon. Okay, it can be represented by epsilon. So it is 180 degree minus coil span. Okay, 180 degree minus coil span. Okay, so now it will be 180 degree minus 160. So it came out to be 20 degree. So the coding angle of this coil BB prime is 20 degree electrical. Okay, I hope it is clear to everyone. So I have told you what is the meaning of full pitched coil and coded coil or the coil span. Is it fine? Now let's take one interesting case. Let's say I have a rotor. Let's say I have a rotor and here I have one pole and here I have the other pole. Let's say this side is north and this side is south. Now let's say I have two sides in the rotor. One side is this, one side is this, and I have one coil, and that coil is housed in this slot. One side in this slot, one side in this slot. Now tell me, what is the mechanical angle between these two sides? Can you tell me? The mechanical angle between these two sides is 180 degree. Okay, and the electrical angle will also be 180 degree. So it means the coil is full pitched coil. This coil is full pitched coil. Is it clear? In two pole, this is the full pitched coil. I hope you understood it. Now I told you about the full pitch coil, meaning of the full pitch coil and short pitched coil. Now let's come to the next thing. Let's say I want to rotate this coil. At this position, how much flux lines are passing through the coil? Can you tell me? How much flux lines are passing through the coil? Tell me, guys. At this position, one side is on the upper side of the rotor and one side is at the lower side of the rotor. How much flux is passing through the coil? It's 5 per pole. Whatever flux lines per pole are leaving, the entire flux is passing through the coil. It means at this time, let's say this time is t equal to 0. At t equal to 0, the entire flux per pole is passing through the coil. Now if I rotate the coil, let's say, if I rotate the rotor, then it will be like this. It will be like this. If I rotate the rotor, the coil side will be like this. Is it fine? Let's say I have rotated the rotor. Now one coil is at this position, one side is at this position, and one side is. Now tell me how much flux is passing through the through this coil. How much flux is passing through? Obviously, the number of lines will be reduced. Okay, the number of lines which are passing between the, these lines, the number of lines which are passing through the coil, they have reduced. Let's further rotate the coil. Let's further rotate the rotor. If I further rotate the rotor, then what will happen, guys? Tell me. If I further rotate the rotor, what will happen? Now the coil location is at this position. Now tell me how much flux will pass through the coil. This side is north, this side is south. Tell me, guys. Now how much flux will pass through the coil? Now the coil sides are, one side is housed here, one side is housed here. Now tell me how much flux will pass through the coil. It's 0. Okay. Now this time no field lines will pass through, no flux lines will pass through the coil, because the coil is itself horizontal. Previously the coil was in vertical, so entire flux lines are passing through the coil, because the coil is like this. Okay, so entire flux lines were passing through, the coil was like this, and entire flux was passing through this. Now the coil has rotated. Now the coil has rotated and become horizontal. If the coil has become horizontal, then no line will pass through the coil, because now the coil is horizontal. This time the coil become horizontal, so no line is passing through this, because every line is passing like this. So now the flux is 0. The flux passing through the coil is 0. So if you want to write, if you are looking at, if let's say you are standing at the coil, you are sitting at the coil, with respect to that coil, if you are looking the flux, then obviously flux is changing with time. At t equal to t1, the flux per pole has reduced. The number of field lines passing through the coil has reduced. Okay, at t equal to 0, the entire phi per pole, whatever the flux per pole was, entire flux per pole was passing through it. Now it has reduced, and now it becomes 0. So it means if I want to write the flux passing through the coil, that will be phi per pole cos of omega t. Is it clear, guys? This is the flux which is passing through the coil. At t equal to 0, you can see that it is the maximum. At t equal to 0, maximum field lines are passing through it. At t equal to t1, you can see that it has reduced. At t equal to, let's say, after some mechanic, at this instant, let's say t equal to t2, this omega t2 become 90 degree. Okay, this omega t2 has become 90 degree at this point. Since it has rotated by 90 degree, no? Mechanical angle, it has rotated by 90 degree. Let's call it omega mt. So omega mt at t equal to t2, omega mt2 become 90 degree. So at 90 degree rotation, the flux lines is 0. So you can write that the phi t, the flux passing through the coil, is phi per pole cos of omega mt. Now what you can do is you can calculate the induced EMF in this coil. So induced EMF in this coil will be minus n d phi by dt. Minus n d phi by dt. Okay. So minus n d by dt of phi per pole cos of omega mt. Is it clear, guys? Is it clear? Tell me, everyone. So now we can calculate the induced EMF in this coil. So it will be equal to minus n phi per pole, and the derivative of cos is minus sign, so it will become plus omega m sine of omega mt. So this will be the induced EMF. This will be the induced EMF in the coil. I hope you understood it. Okay, n phi per pole omega m sine of omega mt. This is the induced EMF in this coil. Okay, now there are so many things in induced EMF. We have to understand many things like, okay, let me tell you, there are some situations when the coil is coded. Let's say the coil is coded. If I say that the coil is coded, then what will happen? Will the induced EMF be like this? And there are some situations where the number of poles are more than 2. Let's take number of poles as 4. If I take number of poles as 4, then what will happen? Let's take full pitch coil. Let's not code it. Okay, let's not take short pitch coil for the time being. Let's take full pitch coil itself and let's increase the number of pole. If I increase the number of pole, then it will look like this. It will look like this. It will look like this. Obviously, there are 4 poles now. Okay. Now there are 4 poles. North, south, north, south. Is it fine? Let's say there are 4 poles now. And at t equal to 0, the coil location is like this. This is a full pitch coil now. You can see that. The mechanical angle is 90 degree and the electrical angle came out to be 180 degree. So now you can see that it's a full pitch coil. In this full pitch coil, we want to know, or maybe at t equal to 0, let's take it here. At t equal to 0, let's call that the position of the coil is one is on this side and one on this side. Now also you can see that the mechanical angle is 90 degree. If the mechanical angle is 90 degree, then electrical angle is 180 degree. It means it's a full pitch coil. How much flux is passing through the full pitch coil? Obviously, it is equal to phi per pole. So at t equal to 0, the flux passing through the coil is phi per pole. So at t equal to 0, flux passing through this is phi per pole. The number of field lines passing through it. The number of field lines will be like this, okay? And you can see that the entire field lines will pass through the coil. So the number of field lines will be equal to phi per pole. At t equal to 0, all the field lines are passing through the coil. Now what you have done is, you are rotating the rotor. Let's say the rotor is rotated. Okay, let me draw the next diagram. At t equal to some other time, maybe after some time, the coil has rotated. Okay, let me draw the this is north, south, north, south. There are 4 poles. And now let's say the coil has rotated by some angle. Now the coil has rotated by some 45 degree, not 45. Let's take it. Okay, let's say that the coil has rotated by 45 degree mechanical. Okay, so the coil, one side of the coil is here, one side of the coil is here. It has rotated by 45 degree. It has rotated by 45 degree. Now, what is the flux per pole? Tell me guys, what is the flux per pole which will pass through the coil? Answer is 0. This time, no flux lines will pass through the coil. It will bypass like this, okay? It will be passed like this, okay? So no field lines will pass through the coil now. Now flux per pole has become 0. The flux has become 0. Is it fine? After 45 degree rotation, the flux through the coil is 0 now. Okay. After 45 degree mechanical rotation, the flux has become 0. Now, can you write the equation of the flux? Can you write with respect to the coil how the flux is changing? At t equal to 0, it is maximum. At t equal to t1, let's say it has rotated by 45 degree mechanical. At this position, flux has become 0. So can I write it like this? Phi per pole cos of omega mt. Can I write it like this? Answer is no. This is wrong now. Why? At t equal to 0, you can see that it is maximum. That's correct. But after mechanical rotation of 45 degree, it has to be 0. But this is not becoming 0. This is omega mt. Omega mt means it's the mechanical angle. Omega m is the mechanical radian per second. Into time, it will become mechanical radian. So this is mechanical radian. So after 45 degree mechanical radian, since it has rotated by 45 degree, after 45 degree mechanical radian, it has to be 0, but it is not becoming 0. Phi per pole cos 45 is not 0. So what I need to write is, now this time I need to write it like this. Phi per pole, flux through the coil will be equal to phi per pole into cos of p by 2 into omega mt. Is it clear, guys? Now you can see that after 45 degree rotation, this angle will become, after 45 degree rotation, this angle will become 45 into 2. 45 into 2 is 90 and cos 90 becomes 0. Okay, and at this position, the flux passing through this is 0. Is it clear, guys? So now if I want to write the flux equation, how much flux is passing through the coil? If I want to write the flux equation, then the flux equation has to be like this: phi per pole cos of p by 2 omega mt. Now I can apply the Faraday's law. Okay, so according to the Faraday's law, the induced EMF will be n minus n d by dt of phi t, flux passing through the coil. That is phi per pole cos of p by 2 into omega mt. Is it clear, guys? Now what you can write is, you can write it like this: n phi per pole p by 2 into omega m into sine of p by 2 into omega mt. Is it clear, guys? This will be the induced EMF in the coil. This will be the induced EMF in the coil. Is it clear? Tell me, guys. Now this p by 2 into omega m, this p by 2 into omega m you can write as omega electrical. Okay, so it will be equal to n phi per pole omega electrical. Let's call it omega itself, not put the subscript as electrical. Let's write it omega itself. Okay, n phi per pole omega sine of omega t. I hope it is clear. Now the induced EMF is this. So remember one point. Remember one point. In the induced EMF, you will always have omega electrical here. Now you'll ask me, you'll say me, sir, but in the previous case you have omega mechanical. In this previous case, the number of poles were 2. The number of poles were 2. It means the mechanical angle and electrical angle are same. It means the mechanical speed and the electrical speed is same. So what you can do is, in the first case, in the previous case also, you can write it like this: n phi per pole into omega into sine of omega t. You can replace this mechanical radian per second in electrical radian per second like this. Because in previous case there were 2 poles only. In 2 poles case, mechanical radian per second is equal to electrical angle per second, electrical radian per second. So you can directly replace it like this. It means always you can say that always the induced EMF will contain electrical frequency. The induced EMF will always contain, whether 2 poles are there, whether 4 poles are there. The induced EMF, you can write always electrical frequency. You can also write mechanical, but then you have to multiply with p by 2. Is it fine, guys? Then you have to multiply it with p by 2. I hope it is clear to everyone. Tell me, say yes or no. Everyone, guys, tell me, is it clear to everyone? Say yes or no. I hope this concept is clear, how the voltage is induced. Now, let's take one more case. Now, what I can do is, let's take one more case. Let me add some slide here. Okay, let me add some slide so that I can teach you one more concept. Okay, let's take a slide. Okay, first let's make it duplicate and then, okay, let's add some slide here. Okay, guys, now let's come back. So I told you how the induced EMF, how to get the induced, how the voltage will be induced. Now let's come back. Let's come to the 2-pole situation. Let's come to the 2-pole situation. Okay, let's say I have 2 poles. One is north side and one is south side, and you have 2 coil sides. One side is this, one side is this. And you know that the induced EMF in this coil will be, this is at t equal to 0, remember, at t equal to 0, this is the position of the coil. And this rotor is rotating in this direction with the omega m electrical speed, mechanical speed. If omega m is the mechanical speed, since the pole are 2, you can say that the electrical speed will also be the same. Okay, now what I can do is, we know that the induced EMF ET will be equal to n phi per pole omega sine of omega t. Is it fine? Now you can see that at t equal to 0, the induced EMF is 0. At this position, induced EMF is 0. And whenever this conductor will come in front of this north and south, after rotation of 90 degree, this side will come in front of north and this side will go in front of the south. At that position, induced EMF will be maximum. Okay, so we have derived this. Now what I want to tell you is, don't look at the induced EMF of the entire coil. Don't look at the induced EMF of the entire coil. Let's divide it in 2 parts. Since every coil has 2 sides, every coil has 2 sides. There is one side on this side and one side on this side. Okay, so let's call it side A side A, and let's call it side B. Side B, okay? So we have two sides, side A and side B. And the induced EMF between these two terminals is this. Now we know that since it has two sides, every side will have equal induced EMF. Every side will have equal EMF, induced EMF. Inside A, what will be the induced EMF? Inside A, let's write the side A induced EMF. Inside A, the induced EMF will be half of that. Let's call it N pi per pole omega by 2 sine of omega t. Is it clear, guys? I can write it like this. This is the induced EMF in side A. What is the induced EMF in side B? In side B, the induced EMF will be half of that again, N phi per pole omega by 2 sine of omega t minus 180 degree. Why minus 180 degree? Because the induced EMF phase will be 180 degree away from one another. Induced EMF in this side and induced EMF in this side should be 180 degree away. Why? Because whenever it is under the north, it will be under the south. If this coil has rotated and come under the north pole, this coil will go under the south pole. It means the induced EMF have the opposite phase. This side induced EMF and this side induced EMF have the opposite phase. If it is sine omega t, it has to be sine omega t minus 180 degree. Now if you want to calculate this voltage difference, now side A minus side B, you can see that the induced EMF ET will be equal to induced EMF in side A minus induced EMF in side B. You will get the same answer. You will get this voltage. Is it fine, guys? You can calculate like this. So please try to understand how I am writing the side induced voltage. Okay, the induced voltage in side A and the induced voltage in side B. I am writing like this. Is it clear? Is it clear, guys? Now, okay. So that's a good point. Now what I want to do is, now I want to make this coil short pitched. I don't want to take the full pitch coil, because in the previous cases, if you look at this case or if you look at this case, I have taken the full pitch coil. I have taken the full pitch coil. Now I want to code the coil, I mean short pitch coil. I want to take short pitch coil. So if I take the short pitch coil, let's see what happens. Let's see what happens. Let's take a rotor. Let's say I have a rotor. I have a rotor, and let's say there are the poles, like there are two poles, north and south. North and south. Now I want to take the coil. So one side of the coil is at t equal to 0. At t equal to 0, one side is here and one side is here. It's not opposite. It means this coil is coded. It means this coil is coded, and you can see that since the pole are 2, there are only 2 poles, so mechanical angle is equal to electrical angle. So at this point, at this position, if the coil side, this side is at this position, then we call it full pitched coil. But since the coil is little bit, the side is little bit shifted from this position, I call it coded coil. This coil is coded. Is it fine? How much angle it is coded? Let's say this angle came out to be epsilon. This angle came out to be epsilon. Is it fine? There are two sides, side A, this is side A and this is side B. Okay, this is side B, and the induced you can see that these two sides are not at 180 degree. There is some small angle, less than 180 degree angle. It is 180 minus epsilon. Okay, 180 minus epsilon. So you can say that this coil is coded. This coil is coded. Now I want to calculate the induced EMF in this coil, the coded coil. What is the induced EMF in this coded coil? So tell me the induced EMF in this coil. Tell me, guys, what is the induced EMF in this coil? This is again same like this, na, side A. So the induced EMF in this coil will be N phi per pole omega by 2 sine of omega t. This will be the induced EMF. Tell me, guys, is it clear? This will be the induced EMF in this side. Now what is the induced EMF in side B? It will be N phi per pole omega by 2 sine of omega t minus, tell me, should I write it minus 180 degree? Should I write it minus 180 degree? No, sir. No, it's not correct. What should I write here? What should I write here? Should I write minus 180 degree? No. Then what should I write? Tell me guys. What should I write? Tell me, what should I write? Previously, the two sides are 180 degree to one another. It means if one induced EMF is on this side, the other coil side has the induced EMF on this side. And if you want to take the difference of this minus this, then it will be added to it and it will become n phi per pole sine of omega t. They are 180 degree to one another. But in this situation, what will happen is if one voltage is on this side, the other voltage will not be exactly opposite. It will be like on this side. Okay, it means this angle between the two sides, in the previous case it was 180 degree. You have to write 180 degree here. But in this situation, the angle is 180 minus epsilon. So I have to write minus of 180 minus epsilon. It should not be 180. Is it fine, guys? Now this will be the induced voltage in side B. This will be the induced voltage in side B. Is it clear, guys? Tell me. Have you understood it? This is side B. Okay. Now we need to take the difference. Now tell me what is the difference. So the difference came out to be, let's call sine as reference. So I can say that it is n phi per pole omega by 2 angle 0 minus n phi per pole omega by 2 at an angle of 180 minus epsilon. Is it fine, guys? Is it fine? Or rather it is minus of 180 minus epsilon. Okay. The angle is minus of minus 180 minus epsilon. This is the angle. Now I need to take the resultant of these two. How to take the resultant of these two? So the resultant of these two came out to be n phi per pole omega by 2 1 angle 0 minus 1 angle minus 180 minus epsilon. You can write it like this. So you have to take the difference of these two vectors. The difference of these two, this length is 1. Let's say this length is 1, this length is also 1. There are two vectors. And I need to calculate this minus this. This vector minus this vector. Now, how to take the difference? How to take the difference? What we can do is, minus of this vector will be on this direction. So this minus this will be equal to this plus this. You can add these two vectors and the resultant will be, you can calculate the resultant vector. So the resultant will be 1 square plus 1 square plus 2 times of 1 into 1 into cos of this angle. This angle is epsilon. Okay. This angle is epsilon. Is it clear, guys? Tell me. I want to take the difference of this and this. This minus this I want to do. So what I can do is this minus this. So take the negative of this. Now it will become opposite to this one. We have to add this vector and this vector. Okay. Now how to add these two vectors? 1 square plus 1 square plus 1 square plus 2 times of 1 into cos of epsilon and take the root of this. This will be the length of the resultant vector. Is it clear, guys? Now what is this length? It will be 2 plus 2 cos epsilon and take the root of this. Take the 2 common. If I take 2 common, it will be 1 plus cos of epsilon and take the root. Is it fine? So it will be 2 cos epsilon by 2. Now this can be represented as 2 cos epsilon by 2. Now tell me, so the induced EMF, will be, ET will be equal to n phi per pole omega by 2 into this. So 2 will cancel, this 2 will cancel, cos of epsilon by 2 sine of omega t plus some theta, because the resultant vector will be at some angle theta. I don't want to calculate that the resultant angle theta, but this will be the magnitude now. So you can see that because of the coding, this voltage has changed. Because of the coding, this voltage has changed. Is it clear, guys? Previously, this voltage was n phi per pole omega. Now, since I coded the coil, since you have coded the coil, the induced voltage will be changed to, the maximum value will be changed to n phi per pole omega cos epsilon by 2. Is it clear, guys? Tell me, is it clear, everyone? So now you can see that because of the coding, the induced voltage has changed. In full pitched coil, in full pitched coil, the induced voltage was N phi per pole omega. This was the maximum value of induced voltage. If you want to calculate the RMS value, divide it by √2. Okay. Now in coded coil, induced EMF, induced voltage is equal to N phi per pole omega cos of epsilon by 2. Is it fine, guys? Now what I do is, now I take the ratio. If I take the ratio, induced EMF in coded coil divide by induced EMF in full pitched coil. In full pitched coil, this has to be cos of epsilon by 2. We call it coil pitch factor, Kp. Is it clear, guys? We call it coil pitch factor, Kp. Induced EMF in coded coil divided by induced EMF in full pitched coil, we call it coil pitch factor, Kp. So whenever you have coded coil, the coil pitch factor will come into picture, and you can see that the induced EMF will be reduced. It will be reduced by this factor. Okay. I hope you understood it. Is it clear, guys? Can I proceed? So I told you what is the meaning of coding factor. Okay, we call it coding factor. We call it Kp. Kp is called coding factor. Coding factor. Okay, whenever the coil is short pitched, the induced EMF will be reduced. Now what I can do is, now let's come back to the flux per pole. So flux per pole, the flux per pole was 4 by P BPLR. This was the flux per pole. Okay. If the coil is full pitched, let's say the coil is full pitched, then the flux per pole at this instant will be phi per, at this instant, at t equal to 0, the flux passing through the coil is phi per pole, directly phi per pole at t equal to 0. After some time it will reduce. Okay. Now let's say that the coil is short pitched. Now let me tell you one more point. Let's say this is north, this is south, and the coil is short pitched. One side of the coil is here and the other side of the coil is here. At t equal to 0, how much flux will pass through the coil? Is it phi per pole? Is it phi per pole? Answer is no. At t equal to 0, the entire flux passing through, entire flux coming out from the north will not pass through the coil, because this coil side is not connected. This coil side is not here. This coil side is shifted from this position. It means the coil is short pitched. Now what is the flux per pole? Can you tell me? The flux at t equal to 0, the phi t is not equal to phi per pole. It will be equal to phi per pole into cos of epsilon by 2. At t equal to 0, this flux will pass through the coil. Okay. At t equal to 0, this flux will pass through the coil. Now if I rotate it, obviously this flux will decrease. The flux passing through the coil will decrease. So if I want to write the expression for phi t, the expression for phi t will be phi per pole cos of epsilon by 2 into cos of omega t. This will be the expression for phi t. This will be the expression for phi t. So if you want to calculate induced EMF Et, that will be equal to N d phi t by dt, and if you want to calculate this, it will be equal to N phi per pole omega cos of epsilon by 2 sine of omega t. So now you can see that now you have a factor of cos epsilon by 2. So the same thing you can write it like this. So the same thing that I have told you in this situation, I have told you whenever you take the coded coil, then the induced EMF will get reduced by this factor cos of epsilon by 2, N phi per pole omega cos of epsilon by 2. This will be the new induced EMF. That same thing you can derive it from the flux per pole, from the phi t, the flux passing through the coil. From that line also, from that concept also, you can derive this expression. Is it fine, guys? I hope it is clear to everyone. Now what I can do is, I can tell you the distribution factor. What is the meaning of distribution? Okay. So I told you what is the meaning of coding. Okay. Now let's come to the distribution factor. Okay, what is the meaning of distribution? Distribution. What is the meaning of distribution? Okay, let's try to understand that. What is the meaning of distribution? Let's say you have a rotor. Okay, let's say you have a rotor and one pole is this and one pole is this. This is north, this is south. Okay, and we have one coil. One coil has n turns like this. Okay, this is my one coil and it has n turns. Okay, this is side A and this is side B. Now the induced EMF in side A will be n phi per pole omega by 2 cos of omega t or sine of omega t. Let's take it sine of omega t, because at this position at t equal to 0 the induced EMF is 0, sine of omega t. Okay, this is the induced EMF in this, and inside B the induced EMF is n phi per pole omega by 2 sine of omega t minus 180 degree, because it is 180 degree away from that. That's why this will be the induced EMF in this. Now what I do is, since the total number of turns are n, what I do is I distribute this coil. It means the n turns coil, I have distributed the n turns coil. It means the entire n turns are not housed in two slots. What I do is I distribute this coil. I distribute it like this. I distribute the coil like this. This side is north pole, this side is south pole. So what I do is I don't put entire n turns in one slot or two slot. Entire n turns in two slots. No, I don't do that. What I do is I distribute the coil. I distribute the coil like this. Some n by 3 in this, some n by 3 in this, and some n by 3 in this. Okay, so I have partitioned the entire coil in three equal parts. Okay, I have make this coil in 3 equal parts, n by 3 in this, n by 3 in this, n by 3 in this. Okay, n by 3, n by 3 and n by 3. So what I have done is I have partitioned the number of turns. But remember, this side is connected with this side because the coil is full pitched. This side is connected with this side because I have to make the full pitch coil. I'm not coding it for the time being. Okay, so this side will be connected to this side, and this side will be connected to this side, and this side will be connected to this side. So the coil is full pitched. Still the coil is full pitched. Okay, so what I have done is I have distributed the coil, and let me tell you one more point. These coils are connected in series. This n by 3 turns, this n by 3 turns will be in series with the next n by 3 turns, will be in series with next n by 3 turns. Okay, so they are connected in series, back to back. There is no removal of the connection. Okay, so they are connected in back to back position, back to back like this. Okay, once one coil is completed, one turns, n by 3 turns are completed. I mean, in the continuity you put n by 3 in this slot, and in the continuity you put n by 3 turns in this slot. Okay, so I hope it is clear to everyone. What I have done is I have distributed the coil. Now what will be the induced voltage? The induced voltage in this side, induced voltage in this side, and induced voltage in this side. What will be the induced voltage? Or rather you can say the induced voltage in this coil, the induced voltage in this coil, and the induced voltage in this coil. What will be the induced voltage? So what we can do is, we know that if the position is like this, the induced EMF ET in the entire coil will be n phi per pole omega sine of omega t. You take the difference, na? This side minus this side. You take the difference, so the induced voltage in the entire coil will be this. Is it fine? Now what I have done is I have distributed the coil. So tell me, what will be the induced voltage in this entire coil? Let's call it coil number 1 prime, or maybe some other name you can put it. Okay, let's call it AA prime. This is AA prime side. This is BB prime. And let's call it CC prime. Now tell me the induced EMF in coil AA prime. So the induced EMF in coil AA prime will be equal to, AA prime will be equal. Now you can see that The previously we have n turns. Now we have n by 3 turns. The position is same. We have n by 3 turns. So you can say that the induced EMF will be n by 3 phi per pole omega sine of omega t. Okay, this will be the induced EMF now. Now what will be the induced EMF in this coil? So it will be induced EMF in BB prime. So BB prime will be n by 3 phi per pole omega sine of omega t minus theta. Why minus theta? Because this side is lagging by some angle. The rotation is on this side, no? Rotation is on this side. It means first the maxima will come in this coil, and then in this coil, and then it means the maxima will lag. First this side will come in front of the north, A side will come, and then after B side will come in front of the north, because B is after A, na? So if this rotor is rotating, first let's say A is coming. If A has come at this position, then after that B will come in front of this in front of this pole, na? So you can say that it is lagging by some angle theta. This angle is theta. What about CC prime? CC prime will lead. Okay, so ET CC prime, it will be equal to n by 3 phi per pole omega sine of omega t plus theta. It will lead. So you can see that this CC prime will come in front of the north pole. Out of these three sides, na? Out of these three coils, CC prime will come first. It will come first. After that, A will, after some rotation, A will come here, and B will come here after that. So it means it will be the first voltage. The maxima will come in CC coil at first, and then in AA prime, and then CC prime. That's why it is plus theta, it is 0, it is minus theta. I hope it is clear. Is it clear, guys? So I told you, if you distribute the coils, the induced EMF will be like this. But we know that the coils are connected in series. So what will be the total induced EMF? What will be the net voltage? Total ET. So the total ET will be equal to, total induced voltage will be equal to ET AA prime plus ET BB prime plus ET CC prime. Since we have coil voltage, these are not the side voltage. These are not the side voltage. These are the coil. This is the coil voltage. So this is the coil voltage, coil AA prime. This is the coil voltage BB prime, and this is the coil voltage CC prime. Now what we can do is we can add them. So if you are going to add them, then you can take n by 3 phi per pole into omega. You can take it common. It will be sine of omega t plus sine of omega t minus theta plus sine of omega t plus theta. Is it fine? You can write it like this. Now what you can do is you take this n by 3 phi per pole omega. You can write it like 1 angle 0 plus 1 angle theta plus 1 angle minus theta. This will be my resultant voltage. This will be my resultant voltage. If the coil is concentrated, if all the n turns are housed in these two slots, we call it concentrated coil. And now the coil is distributed. Due to distribution, the total voltage will be like this. Now we need to add them. 1 angle 0 plus 1 angle theta plus 1 angle minus theta. This is at theta, this is at minus theta. This is 1, this is also 1, this is also 1. We need to add them. How we are going to add them? You can add them, no? You can add them. So the resultant will be 1 plus, let's add these two vectors, no? You can take theta as anything, no? Like 30 degree or 40 degree or maybe whatever, okay? It will depend on the slot change. How much slope, if the one side is in this slot, one part of the coil is in this slot, then the other part of the coil is in these slots. So what is the change in phase? Okay, how much angle has shifted? That angle we have to calculate, and let's call that angle as theta. So if you want to add them, the resultant will be 1 plus root of 1 plus 1 plus 2 times of 1 into 1 into cos of 2 theta. Okay, this will be the resultant, guys. This one I have written like this, plus the resultant of these two vectors. Resultant of these two vectors will be again in this direction. So it will be 1 plus 2 times of this into cos of angle between them, cos of 2 theta. So it will be 1 plus root of 2 plus 2 cos 2 theta. Okay, what you can do is 1 plus root of 2 into 1 plus cos 2 theta. Now you can take the sum. So it will be 1 plus root of 2 into 1 plus cos 2 theta is 2 cos square theta. So it came out to be 1 plus 2 cos theta. 1 plus 2 cos theta. Is it fine, guys? This is the resultant length. So now you can see that the total voltage will be equal to N phi per pole omega by 3 into 1 plus 2 cos theta into sine of omega t, and the resultant angle will be at 0 degree again. This will be the induced voltage now. This will be the induced voltage. If you do the distribution, if the coils are distributed, then this will be the resultant voltage. This will be the total voltage induced in n turn coil. Now the coil is not concentrated, okay? This coil is distributed. You can see that if theta is 0, if this theta and this theta is 0, let's say, then all the turns will be at one position. We call it concentrated coil. If this theta is 0, it means this n by 3 is again in this slot, this n by 3 is again in these slots. So you can say that the coil will become concentrated. If this theta becomes 0, then this will become 3 and this will also be 3, this will cancel, and the resultant voltage will be N phi per pole omega sine of omega t. It means this expression is correct. From this expression, you can take, you can check, if you put theta equal to 0, you will get the same like this, okay? So now you can say that this is the induced voltage in distributed coil. Now what we have is, now we have one term we call distribution factor, like we have coding factor now. Similarly, we have distribution factor KD. KD is called distribution factor. Distribution factor. Now, how to calculate that? The Kp was pitch factor, and the Kp was induced EMF in coded coil divided by induced EMF in full pitched coil. Similarly, the distribution factor will be induced EMF in distributed coil divided by the induced EMF in full pitched coil. Induced EMF in full pitch, concentrated coil. Okay. So KD will be induced EMF in distributed coils divided by the induced EMF in concentrated coil. So what is the distribution factor now? Tell me, guys, what is the distribution factor now? KD will be equal to induced EMF in distributed coil. This is the induced EMF in distributed coil divided by the induced EMF in full pitched concentrated coil. So this N phi per pole omega will cancel. Okay. So it will be equal to 1 plus 2 cos theta divided by 3. This will be my distribution factor now. Okay. This will be my distribution factor. Is it clear, guys? Tell me. Have you understood it? Say yes or no. Tell me, everyone. I hope it is clear. What is the meaning of distribution factor and what is the meaning of coding factor? So it means due to the distribution factor, due to this distribution factor, you can see that the induced EMF will get reduced. This is less than 1. 1 plus 2 cos theta upon 3 is less than 1. So because of that, the induced EMF will get reduced. Okay. You can see that if the coil is concentrated, this was the induced EMF. If there is a distribution, then the induced EMF will get reduced by this factor. Is it fine? So we can say that similarly, the pitch factor will also reduce the voltage, the induced EMF. So let's say if the coil is also distributed and coded, if I take the coil to be coded as well as distributed, then what will happen? Then obviously the induced EMF will get reduced by the Kp and Kd factor. So what you can do is then the induced EMF will be equal to, Et will be equal to N phi per pole omega into Kd into Kp. Both the factor you have to take. This will be the max value of the induced EMF. Is it fine? Let's say you have n turns and the coil is also distributed and the coil is also short pitched. Okay, then you have to take this as the induced. This product I call it winding factor, N phi per pole omega into Kw. Kw is called winding factor. Kw is winding factor. Winding factor. Is it clear, guys? So I told you the meaning of winding factor. What is winding factor? So this has to be the winding factor. Okay, Kd into Kp I call winding factor. Kd is distribution factor, Kp is coil pitch factor. Okay, now let's come back. So I told you the meaning of Kd and Kp and how to calculate, but there is a formula for Kd and Kp and I am not going to derive it. You all the time you can't derive it like this. No, you can't do it like this. This is the process I told you how to understand this how to understand the meaning of distribution. Now in this situation you can see that there is no, I mean, no, the number of phases are not there, number of slots are not there. Okay, so nothing is provided to you, but there are some situations in which the number of poles are there and number of phases are also there and the number of slots are also there. Then you can directly derive the formula for Kd and Kp. You can directly derive the formula for Kd and Kp. Okay, how to derive that? How to derive that? I am not going to derive the formula, but let me tell you the formula for Kd and Kp. Before that, I want to tell you one more point. And that point, for that point, I have to add some slide. Okay, let's add some slide here. Let me add some slide. Let's add some slide. Are you enjoying, guys? Tell me. Are you getting my points? Tell me, everyone, are you enjoying? Okay, I have added 2 slides. Okay, now I told you, okay, that's fine. So I told you what is the meaning of distribution, okay, and what is the meaning of coding. Now let's say I have the rotor and there are poles north and south. Okay, and let's say these are the slots in which the coils are housed. Let's say these are the slots. These are the slots in the rotor. Okay, now what is the angle between the adjacent slot? How to calculate that? How to calculate the electrical angle between these 2 slots? Now what you can do is, we know that the total mechanical angle is 360. Out of 360 degree, let's say there are some number of slots, n number of slots, let's say, or whatever. Okay, so if I divide 360 divided by number of slots, if I divide 360 degree divided by number of slots, then you will get this angle, mechanical angle, this mechanical angle. I mean the angle between 2 adjacent slot. We need to calculate that now. So what you can do is, let's say the total angle is 360 degree, divide by the number of slots. You can count the number of slots and you can divide it like this. So you'll get this angle. We call it angular slot pitch. We call it angular slot pitch, but this is the mechanical angle, guys. We want the angle in electrical form. So what you can do is, you can multiply this with P by 2. You can multiply it with P by 2. You can multiply it with P by 2. Is it clear, guys? Is it clear? We can multiply it with P by 2. We call it angular slot pitch. We call it angular slot pitch. We call it angular slot pitch. Is it clear? Gamma. We call it gamma. Angular slot pitch, gamma. Okay. So this is my angular slot pitch. Angular slot pitch means it is the electrical angle between the adjacent slot. We call it angular slot pitch. There is one more term that I want to define is slots. I want to define this Q. Q is called slots per pole per phase. Number of slots per pole per phase. Okay, now how many slots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's say there are 14 slots. If there are 14 slots, what is gamma? Gamma is 360 divided by 14. This is the slot, this is this angle, mechanical angle, multiply by 180 by P. 180 by, multiply by P by 2. Multiply by P by 2, okay? This will be the electrical angle. We call it angular slot pitch. Now what is Q? Q is number of slots per pole per phase. It means it will be equal to number of slots divided by the number of pole into number of phase. We call it Q. We call it Q, slots per pole per phase, or the number of slots per pole per phase. So we have defined two terms, Q and gamma. Now there is one more term we call phase spread. Phase spread. We call it phase spread. What is phase spread? Phase spread is sigma. We call it Q gamma, the product of this Q and gamma. Now what is the meaning of Q and gamma? If you multiply Q and gamma, you can see that sigma will be equal to, Q is number of slots per pole per phase, multiply by gamma. Gamma is 360 degree divided by number of slots into pole divided by 2. Is it clear, guys? So now you can cancel this. This will be cancelled. So it will be equal to sigma divided by 180 by number of phase. This is called the phase spread. This is called the phase spread. Okay? This is called the phase spread. Let's say your machine is of single phase winding. Your machine is of single phase. If you are taking single phase, then phase spread will be 180 degree. What is the meaning of this? The meaning of this is, let me tell you the meaning of this. What is the meaning of phase spread? Let's say you have an alternator or maybe some generator. It's a single phase generator. If it is a single phase generator, then what you need to do is, you need to check the phase spread. What is the meaning of phase spread? You have to wound the rotor. You have to put the winding in the rotor for single phase. So in single phase winding, the phase spread will be 180 degree. It means from this point to this point, if you look at this side, on this side you can put the one side of the single phase winding. You can put the one side of the single phase winding. For 180 degree, you can put the one side of the single phase winding, and you can distribute the windings like this, okay? And the other side of the windings. It means you can see that this is for entire one phase. These coils for entire A phase. And this is one side of the A phase winding, and this is the other side of the A phase winding. So this will be the phase spread of the winding. This will be the phase spread. Now, if you go for three phase, in three phase alternator, what you need to do is, let's say this is my rotor, okay? In three phase alternator, let's call it AA prime, and this is BB prime, because after 120 degree, because this side is AA prime, let's say, at 120 degree from this position, you have BB prime. You have BB prime. Further 120 degree, you have CC prime, okay? You have CC prime. This is my C side and this is my C prime, okay? So we have AA prime coil, BB prime coil and CC prime coil. Now you want to distribute the coil. These are the full pitched coil. Now you want to distribute the coil. If you want to distribute the coil, now tell me, what is the mechanical angle? The mechanical angle is 360 degree, and how many phases are there? 3. So it's 120 degree per phase. You can say that one phase can use 120 degree. Out of 360 degree, one phase can use 120 degree. If you are willing to distribute the coil, if you want to distribute the coil, then you can distribute one phase in 120 degree angle only. In 120 degrees, 60 degree for one side and 60 degree for other side. Is it fine? So if you want to distribute this coil, you can use 60 degree on one side and 60 degree on other side. Is it clear, guys? So that 60 degree I call the phase spread, okay? 60 degree I have used on this side and 60 degree I am going to use on this side. This is called the phase spread. This is called the phase spread. And you can calculate the phase spread like this. Divide by number of phases. Divided by 3. You'll get 60 here. So the meaning of phase spread is per phase. If you are looking per phase, how much angle is covered? Per phase, how much angle is covered in entire 360 degree? You calculate that. Out of that, one side, how much angle is taken by one side of a coil? If you want to distribute the coil, how much angle is taken by one? Let's say you have 3 phase. So in 3 phase, per phase, how much angle is required? It's 120 degree. 120 degree is required per phase. It means the one phase winding will require 120 degree. Out of this 120 degree, 60 degree for side A and 60 degree for side A prime. That's why the phase spread will become 60 degree only. Is it clear, guys? Have you understood it? Now for single phase, let's say. For single phase, the entire 360 degree divided by 1. It means you can see that for single phase winding, let's say you are willing to wound this induction motor in single phase case. You want to make it single phase alternator. You want to make single phase generator. So you have only one phase. In entire space, you have to put one phase. So it means for one phase, 360 degree is available. Now out of this 360 degree, for one side you have 180 degree. For one side you have 180 degree and for the other side you have 180 degree. So the phase spread is 180 degree. Okay. So the phase spread came out to be 180 degree. Please try to understand the meaning of phase spread. Now can you tell me the phase spread of 2 phase winding? It's 90 degree. Okay. Phase spread for 2 phases is 90 degree. Okay. How to calculate that? Let's say I have the rotor. In this rotor I want to wound it for 2 phase. I want to wound this rotor for 2 phase. Okay. Now the entire angle is 360 degree. You can take it as electrical. Entire angle is 360 degree electrical because 2 poles are there. So out of this 360 degree, there are 2 phases. So per phase, how much angle is required? Per phase you require 180 degree. It means for 180 degree phase A coil should be there, and for the other 180 degree phase B coil should be there. But out of that A phase coil, 90 degree is required for one side, 90 degree is required for one side, and the other 90 degree is required for the other side if you want to distribute. Okay. Is it fine, guys? So this is phase A coil. So the phase spread has to be 90 degree. Phase spread means how much angle is required for one side of a phase. How much angle is required for one side of a phase. Is it clear, guys? So this way we can calculate the phase spread sigma. So I told you some new terms. Phase spread, what is the meaning of phase spread? How much phase is spread? If you want to distribute the coil, then how much spread of a single phase is there? Okay. If you want to distribute the coil, then how much phase you can spread? Okay, we call it phase spread. And there is one more term, angular slot per pole per phase, Q. Q is called the slots per pole per phase, and angular slot pitch, gamma. Gamma is called the angular slot pitch. Okay. I hope it is clear to everyone. Now I can define KD and KP. Now I can define KD and KP. Now I can derive the KD and KP, but I don't want to derive it. I am going to tell you the formula for KD and KP. So KD will be equal to, let's not look at this. KD will be equal to sine of Q gamma by 2 divided by Q sine gamma by 2. Directly you can write the KD like this. You can write the KD like this. Okay. And KP is equal to cos of epsilon by 2. This is called coil pitch factor. So this is KP, this is KD. You know the value of Q, you know the value of gamma, and you can calculate the KD. I hope you understood how to calculate the distribution factor and how to calculate the pitch factor. Now the question is, if you know the number of slots, if you know the total number of slots, let's say you have this rotor, let's call it north, let's call it south. If you know the total number of slots, let's say, okay, and if you know the number of phases, if you know the number of slots and number of phases, if you know the number of slots, number of phases, then you can easily calculate Q and gamma. Okay. You can easily, and the number of pole, obviously, number of poles. If you know these three quantities, then you can easily calculate Q and gamma, and you can put in the formula, you can calculate the distribution factor. There is no problem at all. But the problem lies when the question come in this type of situation. Let's say you have a coil which is concentrated. Now you have distributed the coil like this. Now what you are going to do? You can't apply this formula. You can't apply this formula because you don't know the phases, you don't know the number of slots, you don't know the total number of slots. Moreover, even if you know the total number of slots, you are not utilizing them. You are not utilizing all the slots. You are partitioning it in three parts. It means there are other slots also, na, which you are not going to utilize. Okay. So you are not utilizing all the slots. And the number of phases are not there. Let's assume that this is a single phase alternator. So let's take single phase alternator, but number of slots are not given. Even if the number of slots are given, you are not utilizing the entire number of slots. So now the formula will not be this. The distribution formula will not be this. Now you have to derive it. Now you have to derive the formula. Okay. That's why I have derived this, and I have told you what is the meaning of distribution. So remember, this formula will not be helpful in that situation that I told you recently. Okay. In that situation, this formula will not be helpful. Okay. You have to go with the basics. Okay. You have to go with the basics, and then you have to derive, you have to calculate the distribution factor. The distribution factor came out to be this. Okay. So be careful, guys. That's why I have spent time on this. Anyway, so I told you how to calculate the distribution factor and how to calculate the pitch factor. But there are some situations in which this gamma, what is gamma? Gamma was this angle, electrical angle between two adjacent slots. We call it gamma. If this gamma came out to be less than 15 degree, if let's say this gamma came out to be less than 15 degree, then I call that machine as, then I call those windings as uniformly distributed winding. Okay, so remember this point. If gamma is less than 15 degree, then we call uniformly distributed winding. Uniformly distributed winding. Uniformly distributed winding. Okay, then we call uniformly distributed winding. In that case, you can change this formula because this gamma is less than 15 degree. It means this gamma by 2 is less than 7.5 degree. So if gamma is very small, then you can take that sine gamma by 2 nearly equal to gamma by 2. Okay, so what you can do is you can say that KD will be equal to, distribution factor will be equal to sine of Q gamma by 2 divided by Q gamma by 2, because that sine gamma by 2 will be nearly equal to gamma by 2. That's why I have replaced it with gamma by 2. Now it will become sine of sigma. Q gamma is sigma. Sigma by 2 divided by sigma by 2. Sigma will be my phase spread. Okay. If the windings are uniformly distributed, you can write it like this. Is it fine, guys? Tell me. Tell me, is it clear? So I told you how to calculate the distribution factor, KD. Okay, whenever the windings are uniformly distributed. Now there are some situations in which this Q is number of slots per pole per phase. Number of slots per pole per phase. This Q is fraction. This is not integer. There are some situations in which this came out to be fraction. So the fraction number can be represented as Sk by Pk. Tell me, guys. It can be represented in numerator by denominator form. Let's say this came out to be 2 by 3. Now 2 by 3 is a fraction number, fractional number. So fractional number, you can write it like Sk by Pk. Tell me, guys. You can write it like Sk by Pk. Okay, Sk by Pk. So this 2 by 3, this will become Sk, this will become Pk. We call it fractional slot winding. We call it fractional slot winding. Okay, we call it fractional slot winding. In this situation, what I need to do is, this formula will not be used. Now the KD formula, I'm not going to derive it, okay. This KD formula will change to this value, sine of sigma by 2 divided by SK into sine of sigma by 2 SK. Okay, just remember this point. Sine of sigma by 2 divided by SK sine of sigma by 2 SK. Okay, just remember. Why I have used this n factor? Why this n is there? Why this n is there? Tell me guys, why this n is there? Why I am using n? Sine of q n gamma by 2 divided by q sine gamma by 2. Q sine n gamma by 2. It should be n gamma. This is not the correct formula, guys. Okay, this should be excuse me, sine of q n gamma by 2 divided by q sine n gamma by 2. It should be like this. Okay, now the question is, why this n is there? Why I have taken n? Tell me guys, what is the meaning of n? N means harmonic, because in the induced EMF you will get the harmonics. From where these harmonics will come? Why the harmonics will come? Tell me guys. Okay, let me tell you why the harmonics will come into picture. Look, this is the flux density wave shape. If this is north, this is south, the flux density is not a pure sine wave. You can see that. In flux density, you have harmonics. You have harmonics. Because of that flux density, the induced EMF will also have the harmonics. The induced EMF will also have the harmonics. Now, let me tell you again. Let me tell you, maybe on this slide I can say, let's say I have this rotor and on one side you have north, on one side you have south. If you plot the flux density wave, let's call this alpha 0. From this alpha 0 position, if I want to plot the flux density wave, B alpha, that flux density wave will look like this. It will look like this. It means this flux density wave has harmonics. It contains odd harmonic sine terms. If you use the symmetry, if you use the Fourier transform, Fourier series, using the Fourier series, you can say that it is an odd function and it contains odd harmonics. So if it contains odd harmonics, then you can say that B alpha can be written as BP1 sine of alpha plus sine of P by 2 alpha. Because this alpha is mechanical angle, I have to write it in electrical angle, P by 2 alpha plus BP3 sine of 3P by 2 alpha plus like this. So it will be fundamental term, it will be third harmonic term. Okay, so these type of harmonic will be there. In flux density wave you have harmonics. You have harmonics. Why I have taken P by 2? Because the flux density wave, in flux density wave you have to, because it's an electrical quantity, that's why you have to take electrical angle. This alpha is mechanical angle. Okay, alpha is taken as mechanical angle. You are measuring alpha equal to 0 here, alpha equal to 180 degree here, alpha. Okay, let's take one more. Let's take, there are so many poles now. Let's take many poles. Okay, let's say there are many poles. Okay, north, south, north. Okay, so there are many poles. Okay, now if there are many poles and if you are saying that at this position alpha is 0 and you are moving like this, so you are changing the mechanical angle and B came out to be like this. So in B it has to be electrical angle, that's why I have used the P by 2 term. Is it fine? So now since B has the harmonics, because of this B you have harmonics in induced EMF. The flux per pole, I told you the formula for flux per pole. The flux per pole due to the fundamental term only was 4 by P BP1 LR This was the flux per pole due to the fundamental term. Now, if you want to calculate the flux per pole due to the third harmonic, if you want to calculate the flux per pole due to the third harmonic, then it will be 4 by 3p BP3 LR. Now, I am not going to derive it, okay? I am not going to derive it. Just remember that every space harmonic, these are the space harmonic. Why I am calling these space harmonic? Because alpha is a space angle, alpha is mechanical angle, space angle. That's why these are the space harmonics. So because of these space harmonics in flux density wave, there will be different flux per pole, and every flux per pole, every harmonic will induce its own voltage. So you can say that the voltage will contain harmonics. I have derived only the fundamental component of the voltage. These are the fundamental, this is the fundamental component of the voltage. But you have third harmonic component as well. You have third harmonic component as well. Okay? You will have third harmonic component as well. So if I want to write the induced EMF due to harmonics, what will be the induced EMF due to harmonics? Let me write it here. Or maybe I can add some slide. Let me add some slide. Okay, now, okay guys, so now I can say that due to the space harmonic, we have induced EMF ET. Due to fundamental component, ET was N phi per pole 1 into omega sine of omega t. This was the induced EMF due to the fundamental component. Now, due to the third harmonic component, the induced EMF in the coil, now I am taking this coil. This is north, this is south, okay, and I am taking this coil. The coil is full pitched and there is no distribution. So if there is no distribution, or better you take the distribution also, and let's assume that the coil is short pitched also. Let's say the coil is short pitched and the coil is distributed. The coil is also distributed. It is short pitched. It is short pitched. You can see that this is the epsilon angle. So this side is connected with this side, and this side is connected with this side, and this side is connected with this side. Okay. So there is a short pitch also, and there is a distribution. So if there is a distribution and coding, then the induced EMF due to the fundamental component will be N phi per pole 1 into omega into kW1. Okay. This will be the induced EMF due to fundamental component. Now, the induced EMF due to the third harmonic component will be N phi per pole 3 into 3 omega into kW3 sine of 3 omega t. Okay. This is due to the third harmonic. Similarly, you have higher harmonic, third, fifth, seventh. These are the induced EMF. Okay. You can write the induced EMF like this. What is phi per pole due to third harmonic? I have told you 4 by 3p BP3 LR. This is the flux per pole due to third harmonic. And kW3. How to write the kW3? So I told you this is the formula for kW. So what you can do is you can multiply it 3 and the denominator also you multiply it 3. Q sine Q n gamma by 2. Now this is not correct because this 2 is not in below the entire term. Okay. This formula is not correct. This formula is also not correct. What you can do is you can write it like this: sine of Q n gamma by 2, and you can replace n represent harmonic. So if for the third harmonic, n will be 3 divided by Q sine n gamma by 2. Okay, you can write it like this. Or if the winding is uniformly distributed, you can write it like this: sine of n sigma by 2. This is not correct. Sine of n sigma by 2, because in this expression he has written the entire term divided by 2. This is not correct. This is not correct. So n sine of n sigma by 2 divided by n sigma by 2. Okay. This is the formula for Kd due to nth harmonic. If you want to write the Kp formula for nth harmonic, it will be cos of n epsilon by 2. This is Kpn. Is it clear, guys? So now you can multiply them and you will get the kW, distribution factor. Let's take some question. Let's take some question on distribution factor and winding factor. Okay, let's take a question. Now I can take a question. Let's say there is a 3-phase star connected alternator. We have 3-phase Y connected alternator. Y connected alternator. There is 3-phase star connected alternator, has 81 slots, 6 poles. It has given 81 slots and there are 6 poles. Okay, that's fine. Double layer narrow spread winding. Double layer winding. Double layer means, I will tell you what is the meaning of double layer. Double layer narrow spread winding. Narrow means uniformly distributed. Uniformly distributed. Uniformly distributed. So double layer uniformly distributed winding with the coil span equal to 13 slot pitches. Coil span is given as 13 slot pitch. 13 slot pitches. What is the meaning of this? I'll tell you. Okay, and the flux density wave. Okay, the flux density wave B theta is given as, B theta is equal to sine theta plus 0.4 sine 3 theta plus 0.25 sine 5 theta. Okay, this is my flux density wave which is provided to you. Okay, it is given in the question. Find the RMS value of the third and the fifth phase EMF in terms of fundamental EMF. It means I need to calculate the induced EMF due to third harmonic, take the RMS value, divide by the induced EMF due to the fundamental harmonic, take the RMS value. We need to calculate this ratio. What will be the ratio of this? The induced EMF due to the third harmonic divided by the induced EMF due to the fundamental component. Okay, I need to calculate this ratio. What is this ratio? First of all, there are 6 poles. There are 6 poles, 81 slots, and the coil span is this. What is the meaning of coil span? What is the meaning of coil span? Using the coil span, you can calculate the coding angle. How to calculate the coding angle? Let me tell you guys. So there are total 81 slots. What is the angular slot? Slot angle, what is the angle per slot? So the total mechanical angle in the rotor is 360 degree. We know that. Okay, the mechanical angle in the rotor is 360 degree. So in 360 degree, you have 81 slots. So per slot, what is the mechanical angle? 360 by 81 into P by 2. This will be the electrical angle per slot. Tell me guys, this will be my theta electrical per slot. It means it is the angular slot pitch. We call it angular slot pitch. Now it will be equal to 360 divided by 81 into 6 divided by 3. Is it 6 divided by 2? Is it clear? I have cancelled with this 3 and 3, 27. Okay. Now this gamma came out to be 360 upon 27. You can cancel it. It's 40 by 3 degree. Is it clear guys? So angular slot pitch came out to be 40 by 3 degree. Tell me guys. Angular slot pitch came out to be 40 by 3 degree. That's correct. Now this is the angle per slot. From one slot to other slot, this is the angle. This is the electrical angle. Now one coil is made up of, one coil has 13 slot pitches. It means the coil span. It means from one side of the coil to the other side of the coil, one side to the other side, one side to the other side, there are 13 slots. There are 13 slot pitches. Okay, so now tell me the coil span. What is this electrical angle? One side of the coil is there and the other side of the coil is here, and the coil span is 13 slot pitches. It means the coil span will be equal to, you can calculate the coil span in electrical angle, that is equal to 40 by 3 into 13. Tell me guys, what should be the coil span? Is it 180 degree? Tell me, is it 180 degree or is it less than 180 degree? Tell me the coil span. So the coil span came out to be 40 into 13 by 3. What is this? Tell me everyone, what is this coil span? Tell me the coil span. Do it fast. Do it fast guys. Tell me what is the coil span. How much angle is this? Coil span. It should be 520 degree by 3. Is it correct? 520 by 3. I think this is correct. Okay, this is my coil span. Now can you calculate the coding angle? So the coding angle you can calculate. Coding angle. Coding angle. Coding angle epsilon. So epsilon will be equal to 180 minus 520 by 3. 180 minus 520 by 3. This will be the coding angle. Now can you calculate this? What should be the coding angle? Tell me guys. What should be the coding angle? Do it fast. What should be the coding angle? Do it fast. The coding angle has to be 20 by 3. 20 by 3 electrical. This is my coding angle. Is it clear? So I have calculated the coding angle. Now the coding factor Kp, Kp1 and Kp3. Let's calculate that. Kp1 and Kp3. Kp1 is cos of epsilon by 2 and Kp3 is cos of 3 epsilon by 2. Okay, please calculate these values. Kp1 and Kp3. Okay, Kp1 came out to be, let me calculate the Kp1. Kp1 came out to be 0.9988. And what is Kp3? Kp3 came out to be 0.9848. Okay, so we have calculated Kp1 and Kp3. Now what I need to do is I need to calculate Kd1 and Kd3. Kd1 and Kd3. How to calculate Kd? Kd can be calculated by sine of Q gamma by 2 divided by Q sine gamma by 2. Now first of all calculate Q. Q is number of slots per pole per phase. Number of slots per pole per phase. Is it clear? So it came out to be 27 by 6 and then cancel it by 3 na. So it will be 9 by 2. You can see that it's a fractional slot winding. It's a fractional slot winding. Q came out to be 4.5. It's a fractional slot winding. But what is Q gamma? Because it is a uniformly distributed winding. So if the uniformly distributed winding, then we can use this sigma, phase spread we can use. Now what is sigma? Can you calculate the sigma? Sigma came out to be 9 by 2 into the gamma. Gamma value is 40 by 3. 40 by 3. Okay. This is cancelled 3. This is cancelled 20. So it came out to be 60 degree. So the phase spread came out to be 60 degree. Since the winding is uniformly distributed, so I can say that Kd will be equal to sine of n sigma by 2 divided by sigma by 2. N sigma divided by n sigma by 2 divided by n sigma by 2. Is it clear guys? I have told you that yes, this is the formula now. Okay, so you can use this formula. Now please tell me from this expression, can you tell me what is Kd1? So Kd1, for Kd1 put n equal to 1. So it will become sine of sigma by 2. Sigma is 60 degree. So sine 30 degree divided by sigma by 2. Sigma by 2 is again, n is 1, sigma by 2 is 30 degree, but you have to write in radian. So in radian it has to be pi by 6. This is my Kd1. Is it clear guys? Is it clear? So we have calculated Kd1 like this. We have calculated KD1 like this. Now what is KD3? Tell me about KD3. What is KD3? So KD3, you can put it 3 here. So it will be sine 90 divide by 3 times of sigma by 2. Okay, 3 times of, so it is pi by 2. In the denominator you have to write in radian. It will be pi by 2. Okay, so now you can calculate the value of KD1 and KD3. So KD1 came out to be 0.955. 0.955. You can check it. 0.955. Okay, and KD3 came out to be 0.6399. This is my KD3. I hope it is clear. So we have calculated KP and KD for fundamental and for third harmonic. Now what is the induced EMF? What is the RMS value of the third harmonic voltage and the RMS value of the fundamental voltage? So the induced EMF will be equal to N phi per pole 1 into omega into sine of omega t. Okay, into kW1. Obviously you have to write kW1 here. This will be the induced EMF, kW1 sine of omega t. This is the induced voltage. This is not the RMS value, this is the max value. Okay, this is the instantaneous value, because I have written the sine omega t also. Na? So what is the RMS value of the fundamental? E1 RMS. That will be equal to N, number of turn per phase, because I am writing the phase voltage. So these are the number of turn per phase. What is phi per pole? Phi per pole is 4 by P BP1 LR. 4 by P BP1 LR into omega into kW1 divided by root 2. Whatever the value is, divided by root 2 is the RMS value of the fundamental. Now, what is the third harmonic voltage? It will be N phase phi per pole due to third harmonic into 3 omega into kW3 sine of 3 omega t. Okay, this will be the induced EMF due to third harmonic. So the RMS value will be equal to N phase phi per pole. Phi per pole is 4 by 3P BP3 LR into 3 omega into kW3 divided by root 2. Okay, this will be the induced EMF due to the third harmonic. Is it clear, guys? So we have calculated the induced EMF due to the fundamental and the third harmonic. Now you can take the ratio. Okay, so if you take the ratio, then E1 upon E3, that RMS value ratio will came out to be, it has cancelled, LR is cancelled, P is cancelled, root 2 is cancelled, omega is cancelled. Okay, now you can see that this 3 is also cancelled here. Okay, this 3 is also cancelled here, this 4 is also cancelled. So in the numerator you have BP1 into kW1. You can see that in the numerator you have BP1 and kW1, and in the denominator you have BP3 kW3. Tell me, guys, is it clear or not? Now what is this BP1? BP1 came out to be, BP1 is given as 1 and BP3 is 0.4. So it is 1 over 0.4 multiply by, what is kW1? kW1 is the product of KP1 and KD1. So it is 0.9988, 0.9988 into 0.9988 into 0.955 divide by kW3. kW3 is 0.9848 into 0.6399. 0.9848 into 6399. Is it clear, guys? Is it clear? So you can check it like this. You can check it like this. 0.399, 0.6399. So you can write it like this and you can calculate this ratio. So this ratio came out to be Please calculate this ratio. Please calculate this ratio. I think this ratio came out to be 1 over 0. Please check it. 0.2643. 2643. It should be the ratio. Okay. I hope it is clear. So I told you how to take the effect of harmonics. Okay. What should be the effect of harmonics? I told you, if there is a harmonic in the space, if the flux density is not pure sine wave, if it has the harmonics, then you can take the effect of the harmonics like this. Is it clear, guys? Can I proceed? Can I proceed? Tell me. Okay, now let's come to the next thing, that is MMF produced by distributed winding. What is the MMF produced by distributed winding? Let's say you have let's say this is the stator. Now this time what I'm doing is I am taking a winding on the stator. Okay, and this is my rotor. This is my rotor. Now what I want to do is, there are n turns. There are n turns. This is one coil. Let's say the current is dot here and the current is cross here. So obviously the current is coming out here and it is going inside this. Now if you want to show the flux lines, since the current is coming out, so the flux lines will be like this. Flux lines will be like this. Due to this conductor, the flux lines will be like this. Is it clear? These are the flux lines. What about this? Due to this, since the current is coming inside, so the flux lines will be like this. So you have to make the flux lines like this. Okay, these are the flux lines. These are the flux lines in this direction. Now what I'm doing is, the total MMF due to the n turns is, tell me the total MMF. The total MMF is, total MMF due to this winding, due to this concentrated winding, is N into I. Okay, and where this MMF is used? This MMF is used to produce the flux. This MMF is used to produce the flux. And we know that the flux is equal to MMF divided by reluctance. MMF divided by reluctance. Now if you look at this carefully, now you can see that the total MMF is N, and mainly the reluctance is shown by the air gap. This is the air gap, na? This is my air gap. So you can say that the reluctance is offered by the air gap only. The reluctance is offered by the air gap only. Now if you follow any loop, if you follow any path of the flux line, in any path you have 2 times of the air. I mean the air gap is coming twice. Air gap is coming twice. You are looking, I mean the flux lines is facing air gap twice. In any path air gap is facing, the flux lines is facing the air gap twice. It means what you can say is, you can say that the total MMF is mainly utilized to maintain the flux in the air gap, because the iron reluctance is negligible, the core reluctance is negligible. So if the core reluctance is negligible, then the reluctance is offered by the air gap, and there are 2 air gaps in any path of the flux. In any path of the flux lines, the air gap will come twice, 2 times. Okay, air gap is coming 2 times. Now what does it mean? It means that half of the MMF is utilized to maintain the flux in this side, and half of the flux is used to maintain the flux in this side. Is it clear? Half of the flux is maintained, half of the MMF is utilized to maintain the flux in this side, and half of the MMF is utilized to maintain the flux in this side. So if I want to open it, let's say, let's cut it. Let's cut the stator. If you cut the stator about this, let's say alpha is 0, let's call it alpha 0. So if I cut the stator, it will look like this. It will look like this. This is my alpha 0 point. This is my alpha 0 point. Okay. So from, let's say this is my positive alpha and this is my negative alpha, and this is alpha equal to 0 position. alpha equal to 0 position. So if you go in the positive alpha side, you will face a dot, and here you will face a cross. Is it fine? Is it fine, guys? Here you are facing a cross, and here you are facing dot. And below that, this is the stator part, and below that you have the rotor part also. No? You have the rotor part. Okay, this is my rotor, and this is my air gap. This is my air gap. So what I did is, I cut this, and I, whatever the cylindrical shape is, I open it like horizontal. Okay, I cut it here and I open it like horizontal, okay. So this is the air gap, this part is rotor, this part is stator. Now you can see that at this point, if you look at this carefully, since the current is going inside, so at this point the flux lines are downward. In the air gap, the flux lines are downward. Here also the flux lines are downward. Here also the flux lines are downward. And then the flux lines are upward. So what you can do is, from this point to this point, the MMF in this air gap, from this point to this point, the MMF is n by 2. So if I want to plot the MMF wave shape, if I plot the MMF wave shape with alpha, okay, so I can say that from this point to this point, the MMF is Ni by 2. Ni by 2 MMF is utilized to maintain the flux from this point to this point. Okay, so this is Ni by 2. Okay, this is Ni by 2. From this point to this point, Ni by 2 MMF is utilized to maintain the flux. Okay, now what will happen after that? After that, Ni by 2 is used. Ni by 2 is used to maintain the flux in this region. So if you move in this direction, you will see that from here to here it is positive Ni by 2, and then it is negative Ni by 2. It means the MMF wave will be a square wave. It means the MMF wave will be a square wave. Is it clear, guys? Now if the winding is distributed, because this winding is concentrated, na? This winding is concentrated. Now let's say I distribute the winding. If the winding is distributed, then what will happen? Let's distribute the winding. Let's distribute the winding. You have this rotor and this stator, and I distribute the winding like this. I distribute the winding like this. Now the winding is distributed. Okay, now the winding is distributed. If you are going to distribute the winding, then the MMF wave, if let's say this is alpha equal to 0 and you are plotting the MMF wave, then the MMF wave will look like this. It will be trapezoidal type of wave. Okay, it will be trapezoidal type of wave. Okay, so we'll look at this type of MMF wave if the winding is distributed. Now the question is, obviously it's a square wave. I'm taking it's a square wave, so it has harmonics. This MMF has the space harmonic with respect to alpha. It has space harmonics. Now I want to calculate the fundamental component of that. So the fundamental component of the MMF will be, I'm not going to derive it. So what you can do is, you can take the MMF like number of turn per phase into the maximum value of the current Im, divided by the number of pole, into 4 by pi into Kw. Okay, Kw is the winding factor because of the distribution. Okay, so this will be the fundamental flux, fundamental MMF per pole. Okay, this is the fundamental value of the MMF per pole. Number of turns per phase, this is the number of turns per phase, and into maximum current, the current in the coil, the maximum value of that current. Okay, divided by the number of pole. Okay, this will be the MMF per pole. This is the fundamental value of the MMF per pole. Okay, due to this conductor. Now obviously there are harmonics. That fundamental term will be cosinusoidal. It will be like this, cosine wave. The fundamental will be the cosine wave. Okay, you can show the fundamental like this, no? This will be a kind of cosine wave. Okay, This will be a kind of cosine wave. This will be my fundamental component, okay? So if you want to write, this is the peak value of the MMF. So the MMF will be the peak value 4 by pi number of turns per phase into Im upon pole P into Kw1 cos of alpha, cos of P by 2 alpha. This will be my fundamental MMF. What about the third harmonic MMF? You can write the third harmonic MMF similarly. You can write the third harmonic MMF because it contains the third harmonic also, no? This contains the third harmonic also. If winding is distributed, then the wave should be like this. Now it contains the third harmonic. So the third harmonic will be 4 by 3 pi number of turns per phase into Im3. So or Im, maybe because I am taking the harmonic in the space, divide by P into cos of 3 by 2 P alpha. Okay, this will be my third harmonic value of the MMF. Okay, so this way you can write the MMF expression. Now let's come to the next thing, and the next thing is rotating flux and the effect of space harmonic. What will be the rotating flux and what will be the effect of space harmonics? How to calculate the effect of space harmonic and the rotating flux? Tell me guys, can I take the break? I think it's been 2 hours and 15 minutes. Can I take the break? Tell me guys, can I take the break? Yes, we can take some 5-10 minutes break. Okay, so let's take a break and okay, let's take a break guys. Let me write it here. So the class will start at it's 6:15, so it will start at 6:30 p.m. So the class will start at 6:30 p.m. okay, the class will start at 6:30 p.m. so I am taking the break. Okay, so let's take a break guys. I'll start at 6:30 p.m. Tell me everyone. Tell me everyone, is audio video clear? Is it clear guys? Tell me. Okay, so let's start the class. So I told you that I had taken the break of 10-15 minutes. So now we can start with the rotating flux and the time and the space harmonic. I told you about the MMF, how the MMF will look like, and how we can tackle the MMF shape. Okay, now what I can do is I can tell you about the rotating flux. Okay, let's say I have a 3-phase supply connected to the stator. Let's say I have this stator and 3-phase supply is connected to the stator. Okay, let's say you have a single phase coil. Let's call it AA prime. First look at the flux due to this AA prime coil. Okay, let's say the coil is AA prime, and we are interested to write the flux expression for this coil. Okay, for this phase A. Let's say this is my rotor. Rotor is cylindrical and the air gap is uniform. Now what I can do is, first of all, I know that the flux is MMF. Flux is MMF divided by reluctance. Flux is equal to MMF divided by reluctance. So I have told you the wave shape of MMF. The wave shape of MMF due to this concentrated winding will be like this. It will be a square wave. I have told you previously that the MMF will be square wave, and this amplitude is Ni by 2. This amplitude is Ni by 2. Now, and this angle is alpha. This angle is alpha. Now, if you look at the fundamental component here, the fundamental component will be like this. This will be the fundamental component of the MMF wave. Okay. And the peak value of the fundamental MMF will be N into I by 2. This is my amplitude. And what is the peak value, guys? The peak value will be 4 upon pi into cos of alpha. Now, what is this I? I is Im sin omega t. So, this I can be replaced with Im sin omega t, because let's say the current in this phase coil is pure sinusoidal current. So, the current is Im sin omega t. So, now you can see that this is my MMF. Divided by the reluctance will be the flux. So, flux due to coil A, phi AA prime, will be equal to, this will become phi per pole cos of alpha into sine of omega t. This will be my flux due to coil A. That will be phi per pole cos of alpha into sine of omega t. Or simply you can write it like this, phi naught, or maybe phi m, you can write phi m, not write phi m, because phi m is very confusing. So let's take it phi per pole only. Phi per pole cos of alpha sine of omega t. This will be the flux due to coil number A. This is the flux due to phase coil AA prime. Okay. Now, this flux is pulsating at some, let me show you why it is pulsating. At some omega t, at some time t1, omega t1 becomes, let's say, 90 degree. At that instant, the flux is like this. It's a pure cosine wave. It's changing with alpha at omega equal to omega, at omega equal to b, at t equal to t1. At t equal to t1, at t equal to t1, this become omega t1. And let's say omega t1 is pi by 2. If omega t1 is pi by 2, sine pi by 2 is 1. Sine pi by 2 is 1. So the flux due to the coil AA prime will be phi per pole cos alpha. And it will move like this. Okay. This is my flux due to the coil AA prime. Okay. This is the flux due to the coil AA prime. At t equal to t1. Now what will happen after t1? After t1, the shape will remain same, only the amplitude will change. At t equal to t2, the sine of omega t2 will change, because at t1 this is pi by 2, sine pi by 2 is 1. Now at t equal to t2, this will be somewhat other than pi by 2, so it will become less than 1. So only thing that will change is the amplitude. Okay, only thing that will change the amplitude. So at t equal to t1, this will be the phi AA prime. At t equal to t2, this will be the flux phi AA prime. At t equal to t3, it will become negative. So you can see that this wave is pulsating wave. This wave is, this wave is pulsating. What is the meaning of pulsating? Pulsating means first this will be north, this will be south. It will increase, it will decrease, and then it will change the direction. Okay. So this will be the flux. On this side, it will be north and south alternatively. You can see that flux will be positive at some time and then it will become negative at some time. And the 0 point will remain fixed. We call it pulsating flux or standing flux. So due to a single phase coil, the flux will be pulsating, or you can say standing. Now what will happen for coil B, for phase B? Let's say for at 180 degree space angle, this is my BB prime phase. So the flux due to BB prime will be, the flux due to the coil BB prime, phi BB prime, that will be equal to phi per pole cos of alpha minus 120 degree. Why I am taking cos of alpha minus 120 degree? Why I am taking space angle 120 degree? Because A and B has the displacement of 120 degree in space. That's why I'm taking 120 degree. And we know that the current in phase B is sine of omega t minus 120 degree. So in phase B, the current is this. Okay, this will be my current. I hope it is clear. So this will be the current and this will be the flux of phase B. Now, what is the flux of phase C? CC prime. If you look at this carefully, the CC prime, then CC prime will be further 120 degree away from the coil B. We call it CC prime. Okay, so now if you want to plot it, phi CC prime will be equal to phi per pole cos of alpha plus 120 degree sine of omega t plus 120 degree. Okay, this will be my phi CC prime. So we got phi AA prime, phi BB prime and phi CC prime. Okay, the flux due to phase A coil, flux due to the phase B coil and the flux due to the phase C coil. Now what is the resultant flux? So the resultant flux will be addition of these. I mean, you can add them together. Okay, so if you want to add them, let's try to and let's try to calculate the resultant flux. Let me add some blank slide so that I can teach you. Okay, wait a minute. Let me add some new slides. Okay. So the total flux will be the resultant flux. Let's come to the resultant flux now. So the resultant flux will be equal to phi AA prime plus phi BB prime plus phi CC prime. If you add them, then this phi per pole will come out. This phi per pole will come out and you'll have sine alpha, you'll have cos alpha into sine of omega t plus, then you'll have cos alpha minus 120 into sine of omega t minus 120 degree, and then you have cos of alpha plus 120 degree into sine of omega t plus 120 degree. This will be my resultant flux. If you want to add them, then the resultant will came out to be 3/2 phi per pole, 3/2 phi per pole sine of omega t minus alpha. Okay, you'll get this. This is my resultant flux per pole, and now it is a rotating flux. Why it is rotating flux? Now this flux is rotating. It means what you are doing is you are calculating the flux due to individual coil. The flux due to individual coil is not rotating, it's pulsating, it's standing flux. The maxima and the 0 points are fixed. Let's say you are looking at the flux due to coil AA prime. The flux due to AA prime is pulsating. It is not rotating, it's pulsating. You can see that the 0 point will remain fixed and the maxima and minima will move on this axis or on this position or on this position. It means this point will remain as north and this point will remain as south. It will increase, it will decrease and then change the direction. So north south will remain at this position. Due to the coil AA prime, the north and south will remain at this position. They will change alternatively and the zero flux will remain at this position. So this flux is pulsating. But if you add all the flux, let's say the flux due to AA coil and then BB coil and then CC coil, if you add them together, then the resultant flux will be 3/2 phi per pole sine of omega t minus alpha. This will be my resultant flux per pole. This will be the resultant flux. Now, it's a rotating flux. Why it is a rotating flux? Why I am calling this flux as rotating flux? You can plot it. How to plot this flux? At t equal to 0. At t equal to 0, let's plot it with alpha, with position. At t equal to 0, if you want to plot this flux, then it will be 3/2 phi per pole sine of alpha with negative sign. This will be my flux per pole, this will be my resultant flux at t equal to 0. So if you want to plot it, it will look like this. It will be a minus sign. it will be like this. Is it fine? Minus 3 by 2 phi per pole sine of alpha, it will be like this. Now after some time at t equal to t1, at t equal to t1 it will be 3 by 2 phi per pole, 3 by 2 phi per pole sine of omega t1 minus alpha. Take minus common, so it will become minus 3 by 2 phi per pole sine of alpha minus omega t1. It means it's delayed version of this. Whatever this version is, it is delayed by omega t1. So at t equal to t1, the wave will get delayed. It will be like this. The resultant flux will be like this. Okay. This will be my resultant flux. It means it has, this maxima has traveled to this direction. This maxima has traveled to this direction. Is it clear, guys? You can see that the maxima has traveled to this direction. It means it's a traveling wave. It is traveling in positive direction. It's a traveling wave. It's actually it's rotating, because this is angular displacement. This is angular angle. This is the angular displacement. Alpha is measured somewhere from here, and alpha is moving like this. In this direction, alpha is increasing. So the flux peak, you can see that the flux peak is moving in this direction. That's why the flux is rotating. So this is the rotating flux we have. Okay, this is the rotating flux we have. Now, if the flux is rotating, what is the speed of the rotation? What is the speed of the rotation? To calculate the speed of the rotation, you can put it constant. Omega t minus alpha, you can put it constant and calculate and take the derivative. If you take the derivative, omega minus d alpha by dt is equal to 0. So from here, d alpha by dt will be equal to omega. This way you can write the speed of rotation. So the speed of rotation came out to be omega itself. It means the frequency of the supply. Whatever the frequency of the supply, whatever the omega is, whatever the frequency of the supply is, with that speed only the flux will rotate. Okay, with that speed the flux will rotate. So this will be the speed of the rotation. So it means the flux will rotate with omega speed. Okay, it means whatever the supply frequency, with that same frequency the flux will rotate. We call it at synchronous speed. We call it synchronous speed. It means this flux will rotate with synchronous speed. Okay, the flux due to three phase will rotate with synchronous speed. I hope it is clear to everyone. Now it's a different method. I don't know from which method you have studied this rotating flux, because there are many methods. There are one more method to understand this same concept. Okay, so I told you how the flux will rotate. Now I have not introduced any harmonics. If you look at this, I have taken the fundamental component of this wave, this MMF wave. I have taken the fundamental component of the MMF wave and the current. The current is Im sin omega t. It means I have not taken the harmonics in the current also, the supply current. Okay. Now what you can do is you can introduce harmonic in supply, harmonic in time, and you can also introduce harmonic in space. You can also introduce harmonics in space. What does it mean? The meaning is, since you have only taken the third harmonic in alpha, the fundamental component in alpha, you can take third harmonic in space. You can also write third harmonic, you can write 3 alpha here. Okay, and let's not take harmonic in time. First, let's consider harmonic in space. Let's say there is harmonic in space, effect of harmonic in space. Effect of harmonic in space. Effect of space harmonic, rather you should write it like this. Effect of space harmonics. Effect of space harmonics. It means what you are doing is you are taking the current as sin omega t, Im sin omega t, but the MMF wave, this wave is cos alpha. Na? Now what you are doing is you are not taking this as cos alpha, you are taking this as cos of 3 alpha. Okay, If you are taking this as cos of 3 alpha, then what will happen? Then the resultant flux will be, here you will get 3 alpha. Here you will get 3 alpha. So the resultant flux will be phi r. Phi r. Let's say due to fifth harmonic you are looking. Due to fifth harmonic, what will be the resultant flux? Due to fifth harmonic, the resultant flux will be phi per pole, 3 by 2 phi per pole 5 sine of omega t minus 5 alpha. You will get like this. This will be the resultant flux per pole, the resultant flux in three-phase machine due to fifth harmonic. Now if you calculate the rotation will be equal to omega by 5. It means this rotating flux, again, this rotating flux will rotate at omega by 5 speed. Omega by 5 speed. So due to the space harmonic, the rotation of the flux will get smaller. Okay, the rotation of the flux will get smaller. It will be less. Okay, the speed will be less. Due to the fundamental, the speed will be omega. If you consider the space harmonic, let's say you are considering fifth harmonic, then the speed will get reduced, omega by 5. It will become omega by 5 due to the space harmonic. Now let's increase the space harmonic. Let's say you take seventh harmonic, it will become omega by 7. Okay, and let me tell you guys, the third harmonic, ninth harmonic, 15th harmonic, these harmonic will not be there, not present. Not present. Just remember this point. Okay, the triplen harmonic will not be there, like third or fifth, like or third or ninth or 15th, odd multiple of 3, they will not be present. If you take the third harmonic, if you take the third space harmonic, then if you calculate the resultant, it will be 0. Okay, that's why the triplen harmonic will not be present in the space. Whenever you consider space harmonic, remember, whenever you consider the space harmonic, the speed will decrease. And let me tell you one more point. I have made a mistake. Due to fifth harmonic, it will be plus here, and the speed will be minus. It means due to the fifth space harmonic, the rotation of the flux will be opposite to the fundamental. Let's say the fundamental is rotating in this direction with omega, then the fifth harmonic, due to the space fifth harmonic, it will rotate by omega by 5. Now there are many students who have not understood this concept. For them, what I can do is I can tell you the easy way. The easy way is, what you can do is, you can remember the speed of flux, that will be equal to, what is the speed of flux due to time and the space harmonic? How can you calculate that? Omega divided by 6k minus 1, or maybe let's take it 6k minus 1. Okay, 6k minus 1, and this speed will be opposite. Or you can write omega divided by 6k plus 1. This will be the speed in same direction, positive direction. Now what is the meaning of this k? What this k represent? K can be taken as 1, 2, 3, 4. What is this 6k minus 1? 6k minus 1th harmonic. It represents the harmonic. Let's say k is 1. If k is 1, it will represent fifth harmonic. So you can put 5 here. If you put k equal to 2, it will become 11th harmonic. 11th space harmonic. Remember, this represents the space harmonic effect. Okay, so whenever you take k as 1 or maybe 2 or 3 or 4 or 5, at 2 you can see that it is 11, at 3 you can see it is 17. So for fifth harmonic, 11th harmonic or 17th harmonic, the speed will be opposite to the fundamental. Okay, because the fundamental is rotating like this. So the fifth will rotate in opposite direction. Similarly, the 11th will rotate in opposite direction, and the speed of rotation will be like this, minus omega by 6k minus 1. But if you take 6k plus 1th harmonic, what is the meaning of this? You can put k equal to 0 here, so it will be the fundamental. If you put k equal to 0, it will be fundamental and the speed will be omega. If you put k equal to 1, then it will become 7th harmonic. So for 7th space harmonic, the speed will be omega by 7. If you put ninth harmonic k equal to, if you put k equal to let's say 3 or 2, if you put k equal to 2, it will become 13. So for 13th harmonic, the speed will be omega by 13th, and again in positive direction. So you can remember this formula. You can remember this formula. And this is due to the space. This k plus 1 is space harmonic. 6 plus 1th space harmonic. Due to the space harmonic, you can see that speed will decrease. Space harmonic. So you just remember. Now you can also calculate the effect of time harmonic. What is the effect of time harmonic? So I'm not going to tell you the entire proof. Effect of time harmonic. Now the effect of time harmonic is, let's say you are considering 5th time harmonic. What is the meaning of time harmonic? First of all, tell me. What is the meaning of time harmonic? The meaning of time harmonic means the supply, whatever supply you are putting in, that supply contain the 5th harmonic, sine of 5 omega t or 7 omega t, because the variation of time is this. This is the variation of with time. So the time harmonic means you are changing the supply frequency. So in place of 5, in place of 1, you take 5th harmonic or 7th harmonic or 9th harmonic. Okay. So if you take the effect of time harmonic, let's say you are taking the effect of 5th harmonic, it means the frequency of the supply is 5 omega. So as the flux. So the flux will also rotate at 5 omega. If you take the 7th harmonic, then the speed will again multiply by 7. But let me tell you guys, since it is 6k minus 1, it has to be minus. Okay. And since 7 is 6k plus 1, it has to be positive. I mean 7 came from 6k plus 1. If you put k equal to 1 and you add 1 to it, then it will become 7. 7 will be 7 can be represented from 6k plus 1, and 5 can be represented. If you put k equal to 1 here, it will become 5. So you can see that 5 can be represented from 6k minus 1 and 7 can be represented from 6k plus 1. So it will be positive and it will be negative. So whenever you increase the time harmonic, the rotation speed of the flux will increase. The rotational speed of the flux will increase. Whenever you increase the space harmonic, the rotation of the flux will decrease. Okay. Now let's say the supply contain, 11th harmonic. And space contain, and space is, let's say, 17th harmonic. Now what is the rotational speed of the flux? Speed of rotation of the flux. Tell me guys. Speed of rotation of flux. What will be the speed of rotation of the flux? Tell me guys. What will be the rotational speed of the flux? If the supply contain 11th harmonic, and if you take space as 17th harmonic, space harmonic is 17th, then what will be the rotation of the flux? To calculate the rotation of the flux, what you need to do is, whatever the speed frequency of the supply, multiply by the time harmonic. So supply contain the 11th harmonic, it means this is the time harmonic. So you just multiply it with 11, divide by the space harmonic. Space harmonic is 17, so you divide it with 17. But the problem is whether it will be positive or negative. It means whether it will rotate in the fundamental direction in which the fundamental was rotating, whether it will rotate in this direction or opposite to that. If it is rotating in the same direction as the fundamental, then I'll take it plus. If it is rotating in opposite direction, then I have to take it minus. Now the problem is, tell me whether it will be plus or minus. How to check it? Look at this 11. This 11 came from 6k minus 1. And this 17. This 17 came from again 6k minus 1. If you put k equal to 2, you'll get 11 here. If you put k equal to 3, you'll get 17 here. And I know that whenever something is achieved from 6k minus 1, you have to take negative sign, whether it is time harmonic or space harmonic. In time harmonic, you can see that if you take 5th harmonic, 5 will achieve from 6k minus 1. That's why the 5th harmonic speed will be opposite to the fundamental. and the seven came from 6k plus 1. If 7 came from 6k plus 1, then the speed of the rotation will be in the same direction as the fundamental. That's why I have to take plus. Now you can see that this 11th came from 6k minus 1. So because of that, you have one minus sign, and the denominator also came from 6k minus 1. So this denominator will also have one negative sign. So negative will cancel, and it will left with the positive sign. It means the speed of the flux, speed of rotation of the flux is 11 omega by 17. This will be the rotational speed of the flux, and it will rotate in the fundamental flux direction, the direction in which the fundamental is rotating. In the same direction, this flux will rotate. Okay, this flux will rotate. Is it fine, guys? Can I proceed? Okay, so I told you in which direction this flux will rotate. I hope you will remember this formula. Okay, because this formula is important, guys. The effect of space and the time harmonic. You just remember it, because it might be possible that some question will come from this. Now let's come to the torque prediction. For torque, you just remember the formula. Okay, so the formula is minus P by 2 mu naught pi RL by G Fs Fr sine of delta Sr. Now what is this Fs and Fr and sine of delta Sr? Actually, we have a rotor, we have a stator of the machine, and we have a cylindrical rotor machine. Okay, in cylindrical rotor we have one stator MMF and one rotor MMF, and the resultant of is this one is Fr. I call this resultant as Fr. This angle is called delta Sr, and this angle I call delta Rr. Okay, so I can say that torque is equal to minus P by 2, P is number of pole, minus P by 2 mu naught pi RL by G Fs, this is small fs, this is my stator MMF, into Fr. Fr is the resultant MMF. Okay, sine of delta Sr is this angle. Now you can also write it like this: minus P by 2 mu naught pi RL by G Fr is the rotor MMF, Fr into the resultant MMF, Fr into sine of delta Rr. This will also be the torque expression. Either you write Fs Fr sine delta Sr or Fr sine delta Rr. Just remember this formula. Okay, this way you can write the torque. Now there is one more formula for the torque using the flux per pole. That is minus pi by 8 P square phi per pole Fs. Fs is the stator MMF into sine delta Sr, or minus pi by 8 P square phi per pole into Fr. Fr is the rotor MMF sine delta Rr. Okay, this way you can write the torque expression. Okay, so remember, whenever you have cylindrical rotor machine, in cylindrical rotor machine, the torque formula will be like this. So in some situation they can ask you this question also. I mean the question based on the torque, and then these values will be provided to you and you can calculate the torque value. Okay, now let's come to the DC machine. So here I have completed the basics of the rotating machine. Now I am ready to teach you about the DC machine. Now let me tell you guys, in DC machine we have one stator and one rotor. In DC machine, this is my rotor and this is my stator. Okay, one is north, one is south. On stator you have the field poles, and to maintain this pole you have to supply the DC. You have to give the DC supply to this. We call it field supply. You have to provide the DC supply to this coil. Okay, we call it IF, and this voltage is VF. We call it field coil. This is my field coil. The field coil. What is field coil? The field coil is the coil in which the DC supply is there. And we call this rotor as armature. Okay, we call this rotor as armature, and in this armature the supply will be given via commutator. Let's say it's a motor. If it is working as a motor, then I have to provide the current to the motor. It means the current should be inward. It should be from the supply to the armature. It means it's going inside this armature. So current will go inside this armature via commutator and the brushes. Okay, via commutator and the brushes. Commutator and the brushes. Via the commutator and brushes, the current will go in the armature. Now, the operational position of the brushes is here. Operational position of the brush is here, but the physical position is not there. Physical position is on this axis. We call it direct axis. Okay, let me tell you the axis orientation. In DC machine, we have north on this side and south on this side. Okay, so what you can do is, we can call this as direct axis. This is my direct axis, D axis. And the perpendicular to this is Q axis. This is my Q axis. You can also call that this axis is GNA, geometric neutral axis, because it's a geometrically neutral point. You can say that this axis will divide in equal halves. That's why I call it geometric neutral axis. Okay, there is one more axis, magnetic neutral axis, MNA. The MNA will be in that direction in which the flux is zero. Now, let's say there is no current in the armature. If there is no current in the armature, then the flux will go from north to south like this. Okay, this is the flux direction. This is the flux direction. Now, in which direction the MNA is? MNA is perpendicular to the resultant flux. So, MNA will lie on this. Okay, this is the MNA, magnetic neutral axis. MNA, and this is also GNA. So, MNA, GNA, and Q axis. For this situation, both are, all the three are same. And this is the D axis, direct axis. So, let me tell you guys, the brushes, where the brushes are present, physically, the brushes are present on D axis. Physical location of the brushes is on D axis, but the operational location will be on Q axis. Okay, remember this point. Now, what this commutator do? So, the commutator, this commutator will, it has two operations. It need to do two things. The first thing is, it will make the rotor MMF stationary. Make rotor MMF stationary. Rotor MMF stationary. Why? Why you need to make the rotor MMF stationary? The problem is, in any rotating machine, the relative speed between the stator MMF and the rotor MMF has to be zero. Let's say this is the DC machine. In DC machine, we know that the stator MMF is fixed. Phi S, stator flux or stator MMF is fixed. If stator MMF is fixed, it's not rotating because north and south pole are fixed. So the stator MMF is fixed. So to make this machine rotatable, to make this machine working, I need to make the rotor MMF to be stationary also. So I have to make the rotor MMF in this direction or maybe some other direction, but it has to be stationary. Relative speed between them should be zero. If this is not rotating, this should also not rotate. Okay, so remember this point. The relative speed in any rotating machine, whether you take DC machine or induction machine or synchronous machine, whatever, okay, in all the machines, the relative speed between the stator MMF and the rotor MMF must be zero. It means if stator MMF is stationary, you have to make the rotor MMF stationary. So the commutator will make this. Commutator will handle this situation. How it will handle, I am not going to tell you because it's not the right time to tell. So the commutator will make the stator rotor MMF stationary. Okay. Now the next thing is, this commutator will act like a mechanical converter. It means in case of motor, it will convert the DC current to AC current. Okay. In case of motor, what will be there? Tell me guys. Let me write it. What this commutator does? It will make DC current. It will make DC current to AC current. It will make DC current to AC current in case of motor. In case of motor, we provide the DC current. Okay, we provide the DC current IA. This is my DC current IA. So what this commutator will do, this commutator will make this DC current into AC current. Okay, this is the first thing. Or in case of generator, inside the rotor you will get the AC, but outside the rotor it has to be DC. Okay, so it will make AC to DC. It will convert AC to DC. The induced EMF in this rotor will be AC. In case of DC generator, this induced EMF in the rotor will be AC, and the out of the brushes, out of the commutator and brushes, it has to be DC. It means it is making AC to DC. So in case of generator, it will act like a rectifier. AC to DC. It means it will act like a rectifier. It will act like a rectifier. Is it fine? In case of generator, it will act like a rectifier. And in case of motor, it will convert DC into AC. Okay, it will act like a converter, DC to AC converter. Okay, so remember this point. The commutator will do two things. One is to make the rotor MF stationary, and the second thing is this. Now there are many students who are not able to understand this point. I understand that. I know that because they have not studied the basic part. So I'm not going to teach you that part because it is not the right time to teach you that. Now let's come to the next thing, the concept of torque and the back EMF in DC machine. Now in DC machine, if you look at carefully, you have the permanent pole north and south. This is the field supply, and this is my armature. Via brushes you provide the current. Via brushes current is going on. Okay, you can see that this is my IA which is going inside it, and it will come out from here. Okay, this is my armature current. Now if you want to draw its diagram, its equivalent diagram, if you want to draw the model of this machine, so depending on the connection of the field supply and the armature, it is of four types. One is separately excited. The second one is separately excited. The second one is shunt excited, or shunt, simply shunt. You can write it shunt. Depending on the connection of the field coil and the armature, we call it shunt, or series, or compound. It can be of four types: separately excited, shunt excited, series, or compound. Now what is this separately excited? In separately excited, the supply for this field and the supply for the armature is different. Let's say you take a motor, DC motor. In DC motor, this will be represented as armature, and this will be my back EMF. Okay, and the field is excited separately. This is my VF, and this current is IF. Okay, so you can see that in DC motor, what I need to do is I need to excite this field separately. Okay, and this is my back EMF EB. This is RA. So in DC motor, the current will come like this, and this will absorb the power. EB into IA, you can say. It will absorb the power, and that power will be delivered to the shaft. Okay, so this is the model of the motor, DC motor. In case of generator, the model will remain same, separately excited generator. The model will remain same. Let's call it A now, EA. Okay, EA, and this will be my field supply. So the model remains same. You can see that the model remains same, and the current direction will be opposite. Now IA will be in opposite direction. IA will be in this direction. Now you can see that the current will coming out from this positive sign. It means this source will deliver the power now. That's why it is called generator. Okay, this is my DC generator. Okay, and this is my DC motor. Now what is this EMF? What is this back EMF? So the back EMF will be equal to, how to calculate this back EMF? This back EMF will be equal to, I'm not going to derive it. This will be equal to PZ divided by 2 pi A phi per pole into omega m. Omega m is the rotor speed in radian per second. Okay, this is my back EMF. Now what is this PZ upon 2 pi A? This PZ upon 2 pi A is KE. KE phi per pole into omega m. Is it fine, guys? This is my back EMF. KE is PZ upon 2 pi A. P is number of pole. What is Z? Z is the total number of conductor. Z is total number of conductor. Total number of conductor. What is A? A is number of parallel path. Number of parallel path. A is number of parallel path. Okay. A is number of parallel path. Phi per pole, you know phi per pole. Phi per pole is 4 by P BPLR. And omega m. Omega m is mechanical radian per second. The speed of the rotor in mechanical radian per second. Okay. So I told you what is omega m, what is phi per pole, and what is A. A is number of parallel path. Now, if the rotor is connected in lap winding or wave winding, if there is a lap winding or wave winding, then depending on that, A will change. A will be equal to 2 for wave winding. For wave winding, A will be 2. And for lap winding, A will be equal to P, pole, number of pole, okay, with lap winding. With lap winding, okay. So depending on type of winding, the parallel path will change, okay. If there is a wave winding in the armature, then we call A is equal to 2, number of parallel path will be 2, and for lap winding, number of parallel path will be equal to pole, P. This will be my back EMF, okay, PZ upon 2 pi A, phi per pole into omega m. PZ, Z is the number of conductor. How to calculate the number of conductor? Number of conductor will be equal to number of turns, total number of turns into 2. Okay, this will be total number of conductor. This way you can calculate the total number of conductor. I suppose it is, I hope it is clear to everyone. Now, how to calculate the torque? How to calculate the torque in the motor? To calculate the torque in the motor, what you can do is you can take the product EB into IA. EB into IA is the power output. Power output, you can say the power output of the rotor. Okay, because this will be the power absorbed. Here the power will be lost. Whatever power is supplied from this terminal voltage VT into IA, in case of motor, V2 into IA is the power supplied by in the motor. Then out of that power, some power is absorbed by this resistance. The remaining power will come out from the rotor, and it will be available at the shaft. So now you can say that the P out will be equal to EB into IA, and P out is a torque into speed. Torque into speed. Now what is this EB? EB is KE phi per pole into omega m into IA is equal to T into omega m. I can cancel this omega m and I can calculate the TE. So the torque expression will be KE phi per pole into IA. So remember this point. This is the electromagnetic torque. This is the torque expression in DC machine, and this is the back EMF expression in DC machine. Okay, so remember this point, guys. You have to remember this point. How to calculate the torque and how to calculate the back EMF. Now, exactly same formula will be used in case of DC generator. In DC generator, this EMF will be KE phi per pole omega m, and in generator we don't look at the torque. In motor we are interested in torque, but in generator we are not interested in torque. Okay, so remember this point that we can easily see that. Okay, so I told you about the concept of back EMF and the torque. So remember these formulas. These formula will help you. So I told you there are 4 type of connection. What are those connection? One is separately excited motor, separately excited generator. Now there is shunt excitation. In shunt excitation, what happens is the connection will be like this. You have this armature. In case of motor, let's say you have this armature, and this field coil is connected in shunt. The field coil is connected in shunt. This is called shunt motor if current is coming like this. Okay, if the supply is delivering the power, let's say current is coming like this, okay, then I will call it motor. Okay, it will be motor. In case of generator, shunt generator, the connection is exactly same. The connection is exactly same. But now in this case, the current is coming like this. I mean, this EA is delivering the current, IA. Out of that, some current will go to the field, IF, and the remaining current will go to the supply side. Okay. So this will act like a generator. So remember, the connections are same, only the current direction is opposite. Okay. In case of motor and in case of generator. This is called shunt motor and shunt generator. Now, in series, what is series excitation? What is series excitation? So in series, the armature is connected in series with the field coil. So the field coil and the armature are connected in series. Whatever current in the armature is, the same current will flow through the field. Okay. So in case of motor, the power will be delivered by the supply. You can see that the supply is delivering the power. Okay. So the power will come like this. But in case of motor, and this will absorb the power. In case of motor, it is absorbing the power. So you can see that in case of motor, this is delivering the power and this is absorbing the power. That power absorbed will be available at the shaft. Now in case of generator, it will deliver the power. In case of generator, it will deliver the power. It will be like this. Okay. This is my EA and the current will come like this, IA. This is RA and this is RF. This is my VT. Okay. So you can see that this is the generator we have, because the current is the power is delivered by this source. So this will absorb the power. I call it DC series generator. So this is my series excitation. Now what is compound excitation? In compound excitation, we have both the windings, shunt and series. We have both the connections, shunt and series. So the connection will be like this. The connection will be like this. Here we have shunt winding as well as series winding. Here we have shunt winding as well as the series winding. Okay. We also have the series winding. Okay. This is called the compound. It will be motor if the current is coming like this. Okay. And going current, some current is going like this and some current is going like this. So we call it motor. And in case of generator, this current will come out. Some will go on this side, some will go on this side. Okay. So this is called compound generator. Okay. And compound motor. I hope it is clear to everyone how the connections will be there. So remember, there are 4 types of connections: separately excited, shunt, series and compound. In compound, we have further 2 types of connection, 2 types of operation in compound. One is cumulative, one is differential compound. Okay. So I'll tell you about the cumulative and differential maybe after some time. But let's proceed. Let's proceed with the next thing. Next thing is armature reaction. What is armature reaction? What is armature reaction and what is this brush shift and effect of brush shift? How to check it? Okay. And what is this compensating winding? So everything is related. Okay. Everything is related. Compensating winding and interpole and the armature reaction and the brush shift. All these things are related, will come under armature reaction. Now, what is this armature reaction, guys? How to understand armature reaction? It's simple. Whenever, let's say you have a motor. Whenever you have a motor, let's say you have a motor. In motor, you are not supplying the current to the armature. Let's say motor is working at no load. So the current taken by the motor is 0. And this is my field supply. One is north, let's say one is south. Now if you look at the flux due to the field, stator flux. So the stator flux will be in this direction. Stator flux will be like this. And since there is no current in the armature, so the resultant flux will also be the stator flux, phi s. This will be my phi s. This will be the resultant flux because there is no current in the armature. Okay. So the resultant flux will be the stator flux only. This will be my stator flux. Now, if the current start coming in the armature, then armature will also give its own flux. Because of that armature flux, the resultant flux will tilt. The resultant flux will change. Now, how the resultant flux will change? Let me show you. Let me show you. Now, I have this rotor. And let's say these are the poles. One is north and one is south. Here you have the brushes, the operational position of the brushes. Okay. Now, on this side, remember, you have the dot. The current is, let's say, dot. And on this side, the current is cross. In DC machine, remember, on one side of the brush, you have the dot. On the other side, you have the cross. This has to be like this. Otherwise, the machine will not work. If, let's say, this conductor come on this side, then the current has to be reversed. From cross to dot. It has to be from cross to dot. Now, who will do that? Commutator and brushes. Both will do that. Why? Because the MMF of the rotor has to be stationary. Because the MMF of the stator is stationary. MMF of the stator is stationary. You can say the MF or flux of the stator is stationary. North and south are stationary. Now, the MMF or the flux of the rotor must be stationary. To make this stationary, one side has to be dot, one side has to be cross. So that the MMF will be in upward direction. Is it fine? So that the MMF of the rotor will become upward direction. Is it fine? Now the relative speed between them will be 0 and the machine will work. I told you, in any type of rotating machine, the relative speed between the stator flux and the rotor flux must be 0. I told you that. So that has to be applicable here. That's why in DC machine, on one side it has to be cross, on other side it has to be dot. It doesn't matter on this side it is dot or on this side it is dot. No, it doesn't matter. But it has to be dot on one side and it has to be cross on the other side. So remember this point. So now what I can do is, let's take this situation first. In this case, there is no current in the armature. If there is no current in the armature, then the resultant flux will be the stator flux only. Now what I did is, I provided the current to the armature. If you provide the current to the armature, then two fluxes will be there. One is the stator flux and one is the rotor flux. So the rotor flux will be in upward direction. You can see that on this side current is coming, on this side the current is going. So if you rotate your fingers, this will be my rotor flux, phi r. So there will be two fluxes now, stator flux as well as the rotor flux. Because of that rotor flux, the resultant flux will tilt. Okay. Because of the rotor flux, the resultant flux will tilt. So the resultant flux will look like this. This will be my resultant flux. Is it fine? In this direction, the resultant flux will be there. It means this flux is not uniform over the pole. Now the flux is tilted. Resultant flux is tilted. So the MNA, the magnetic neutral axis, will be perpendicular to this. This will be my MNA now. MNA. And GNA will remain on this position. GNA will remain on this position. Okay. This is my GNA. GNA will remain on this position. GNA will remain on this position, but the MNA will tilt. MNA will tilt in this direction. Now, because of the armature reaction, the flux will tilt and the flux will tilt, and the problem is, look, on this side of the pole, the flux is reduced. On this side of the pole, the flux is increased. But the problem is, the number of lines which has reduced on this side will not be equal to the number of flux lines which has increased on this side. Okay. The increment is less than the decrement. Let's say there were 50 lines here and 50 lines here. So all the 50 lines should come to this position. Now it means it should be 100 lines now, but it is not actually. It will be 90 or something else, or something less than that. Why? Because of the saturation. Because of the saturation of this pole tip. Because of the saturation, you can see that the number of flux which were previously, which was there, the number of field lines which were there in this case, now that flux is reduced because of the saturation. This side is saturated now. Okay. So you can say that due to armature reaction, the flux will be tilted, the resultant flux will be tilted, and the flux will get reduced. The flux will get reduced. Also, the flux will be distorted. The flux wave will be distorted. The resultant flux wave will be distorted. I'm not going to tell you how it is distorted, but remember the flux wave will get distorted due to the armature reaction. Okay. Now let me tell you one more point so that we can clear it in a simple way. In which direction the motor will rotate? Let's say this is my DC machine. This is my DC machine, and let's say this is my north pole, this is my south pole, and on this side you have cross. The current is cross on this side and dot on this side. And let's say the machine is working as a motor. The machine is working as a motor. This machine is working as a motor. If this machine is working as a motor, in which direction it will rotate? Tell me guys, in which direction it will rotate? How to check it? To check this, check the rotation of the motor, what you can do is you check the direction of the torque. If you get the direction of the torque, then in that direction only the motor will rotate. In the direction of the torque, the motor will rotate. So we need to calculate the direction of the torque. Once you get the direction of the torque, then easily you can say that in that direction only the motor will rotate. Now the question is, in which direction the torque, what is the torque direction here? To look at the torque direction, we can see that we can calculate the force on this conductor. In which direction the force will be there? Tell me guys. To get the force, we know that the force is IL cross B. This is the formula for force. Now tell me, at this position, B is in this direction. B is in this direction. And the current is cross. The current is cross. Current is inside this. Current is going inside it. So tell me, if current is inside, L is also inside. And if you take L cross B, so L is inside and B is in this side. So force will be downward. So on this conductor, the force will be downward. On this conductor, the force will be upward. Why the force will be upward on this conductor? Because the current is dot and B is again in this direction. Magnetic flux is going in this direction. Okay. So B is in this direction and current is dot. Dot means coming out. So if you try to calculate the force on this conductor, the current is coming out. So L is also in this direction. L is in this direction and B is in this direction. So L cross B will be the force. Okay. So here the force will be upward. So on this side of the conductor, the force is upward. On this side of the conductor, the force is downward. So it means the torque will be in this direction. This will be the torque direction. If it is motor, it will rotate in this direction only. Is it fine? It will rotate in this direction only. So this way you can calculate the direction of the rotation of the motor. Fine. If you know the direction of the okay. Tell me guys, is it clear? Is audio video clear? Tell me everyone, is audio video clear? Is audio video clear? Okay, let's come back to the so I told you, let's say if it is motor, it will rotate in the direction of the torque. So this direction will be the torque direction and the motor will rotate in anti-clockwise direction. Now if this machine is working as generator, if this machine is working as generator, in case of generator, the direction of the generator will be opposite to the torque, opposite to the electrical torque. If this torque in this direction and the machine is working as generator, then the machine will rotate in this direction. Okay, so this is the generator direction rotation. This is generator, and this is the motor rotation direction. This is motor rotation. If this machine is working as motor, it will rotate anti-clockwise. If this machine is working as generator, it will rotate in clockwise direction. Just remember this point. Okay. Okay. Okay, let's come back to the concept again. So I told you the direction of the machine, in which direction the machine will rotate. Let's come back to the armature reaction again. Tell me, in this situation, in which direction the motor will rotate? On this side, the current is dot, and on this side the current is cross. Now tell me, in which direction the motor will rotate? Tell me the rotation of the motor. In which direction the motor will rotate in this question, in this case? Tell me the direction of the rotation of the motor. In which direction the motor will rotate? Tell me, guys. In which direction the motor will rotate? Tell me. Here in this direction, in which direction the motor will rotate? Tell me, guys. So what you can do is, the B is in this direction, and look at this. This is the dot current. This current is dot. It means the current is coming out. So the force will be IL cross B. So L is towards you and B is in this direction. So L cross B is upward. So you can say that this side will be, on this side the force will be upward, on this side the force will be downward. So you can say that the electromagnetic torque is in this direction. Electromagnetic torque is in this direction. So if this machine is working as motor, it will rotate in this direction. It will be clockwise. Okay. For motor, it will rotate in clockwise direction. For motor, it will rotate in clockwise direction. And for generator, it will rotate in opposite direction. For generator, it will rotate in opposite direction. Fine. For generator, it will rotate in opposite direction. For generator, it will rotate in opposite direction. Now let's look at the effect of the armature reaction. The effect of the armature reaction is tilting of MNA, rotating of MNA in the direction opposite to the motor rotation. So the effect of armature reaction is rotating the MNA in the direction opposite to the motor rotation. It means the direction in which the motor is rotating, MNA is tilted opposite to that. MNA is shifted opposite to that. Okay. Due to armature reaction, MNA is shifted from GNA, because now in this case, if you look at this, this is my GNA and the same will be the MNA. Same will be MNA. So MNA and GNA are same in this direction. But the problem is, due to armature reaction, you can say that the GNA will remain same. GNA is fixed. It's a geometric neutral axis. But the magnetic neutral axis will be shifted. Now it will be shifted in opposite to the motor rotation. Motor is rotating in this side. Let's say this machine is working as motor. So motor is rotating on this side. So MNA will be shifted in opposite rotation, opposite direction. Or if this machine is working as generator, then MNA is shifted in the direction of generator. You can say that. Is it fine? So remember, the effect of the armature reaction on MNA and GNA is like this. I told you, and the next thing is, I told you that due to armature reaction, the flux will get reduced. Okay. Why it will get reduced? Due to saturation. Due to saturation effect, the flux will get reduced. Okay. So this is the effect of armature. Now, there is more problem which will come if this armature reaction is high. Let's say the current is high. Let's say the load current is high, or the armature current is high. If this armature current is high, more the armature current, more will be this rotor flux. More will be the rotor flux or armature flux. And if the armature flux is high, then the tilt will be again high. Then the tilt will be more, the tilt will be higher. The MNA rotation will be higher. So more the armature current, more will be the tilt. Okay. And the wave will get distorted. The flux wave, the resultant flux wave will get distorted. So remember, these are the bad effect of the armature reaction. Now, how to avoid the armature reaction effect, and what will what will be the brush shift, and there are so many topics that we need to study, but the time doesn't allow, and moreover, I'm not feeling well actually. My health is not with me, so that's why. Let me tell you which other things I need to tell you about. The effect of brush shift I need to tell you, and then compensating winding and interpole. So there are so many things that I want to tell you about in DC machines, and then operating characteristics of DC generator. These are the important topics, guys. Okay, so these are the important topics that you need to study. Voltage build-up process in shunt generator and then in series generator. Okay, so there are so many things in DC machine which I want to tell you, and but let's stop it here, because first of thing, that the number of students are not that much high, and the second thing is I'm not feeling well actually. Okay, so now I want to stop it. So in today's class, what I have covered is, let me tell you, I'll take some other dedicated session on DC machine. In that I'll cover it. So in today's class, I have told you about the basics of rotating machine. Okay, I have told you what is the meaning of electrical and mechanical angle, and then I have told you about the coil span and coded coil. Okay, and then I told you about the induced EMF. Okay, I told you about the induced EMF, and then I told you about the induced EMF in the coded coil, and then I told you about the distribution. What is the meaning of distribution, how to calculate the distribution factor. Okay, and then I told you about the distribution factor and the coil pitch factor. Okay, and then we come to the induced EMF due to harmonics. Okay, and then we solved one question. After that, I came to this MMF produced by distributed winding. Okay, and then I told you about the effect of the space and the time harmonic on rotating flux. Okay, and then I told you about the torque expression, and then I entered into DC machine. Okay, so DC machine I have not covered completely, so I think we should stop it now. So maybe in the next session I'll take one dedicated session on DC machine. In that session I'll cover the DC machine and the synchronous machine. Okay, because I told you that it's not possible to cover entire things. If you want to teach you, or if you want to make the student understand something, then it will be difficult to cover everything in 3 hours or 4 hours. The problem is, I try to teach you that MMF now, because I understand that many students don't know this. Many students have not studied this, how this MMF wave will look like, and how I have written this flux purpole, the flux due to the phase A coil. So these things are not understood to many students. They cannot understand, because they have studied in a different way. So if I want to teach you how this came, then it will take some time. It will take some time. So in 4 hours, you cannot complete the entire syllabus or entire things. So what I will do is, I will take one dedicated session on DC machine and one dedicated session on synchronous machine, and in that I'll cover that. Okay, I'll cover it. So till then, you can take care and keep revising the important topics. Okay, so that's all for today's session, guys. Don't forget to subscribe our channel and install this mobile app, and press the bell icon so that you get the notification. Okay, so it's okay, and thank you for showing interest in this class. From tomorrow onward, we will take a revision of power electronics, and there are 2 classes of power electronics. Tomorrow also, tomorrow's class I'll take from 10 a.m. to 2 p.m. So don't forget to attend that class also. And in that class, I will revise the phase controlled rectifier. In the next class, I'll try to revise the DC-DC converter and inverter. Okay, so I will revise only 3 topics. Okay, one is phase control rectifier, and in the next class I'll try to cover the DC-DC converter and the voltage source inverter. The inverter topic I'll take. Okay, so that's all for today's session, guys. See you tomorrow at 10 a.m. Power electronics is there. I hope that maximum student will join that class, because if the number of students are higher, then also it will provide the more energy to the teacher. Okay, so if the number of students are not higher, if the number of students are not that much, so that's why the energy is very low. Okay, if you are not replying, or if you are not taking interest, or if the number of students are less, then obviously it's not good for the teacher. It doesn't mean that the knowledge of the teacher is less or something else. It doesn't mean that. It means that I mean, the teacher is not feeling well because the doubts are not coming, the students are not replying. That's the main problem. Anyway, so I will cover the remaining topic in some dedicated session. So see you in the next session, guys. Okay, take care and bye.